All right, so looking at the schedule, and we're pretty much adhering to schedule. Okay, so today is Tuesday, September 15th, day 9. We're going to start chapter 2, although that's not going to be due at the chapter 1 homework. So bear in mind that the homework for both chapter 2 and chapter 3, this is for a big midterm. This used to be for a big midterm. All this stuff will be due at the homework 2-3, well, the day after the homework 2-3 session, all right? So the stuff we cover today won't be due until Friday, October 9th. Okay, and by then I'm going to get some grading done finally, by the way. Okay, as I've mentioned, the next couple weeks will be very tough with grading. So I'm going to have to play catch up at the end of the month. Okay, now, so remember that only chapter 1 is going to be due on Friday. So let's see here. So only the stuff from chapter 1, 1.1 to 1.10, 1.11 is optional. So chapter 1 will be due on this Friday, which is September 18th. And that's chapter 1 only. Although I do encourage you to keep up with chapter 2. I suspect you'll be working on this this upcoming weekend, or I hope you will. Okay, well, we do want to get a head start. And the stuff we do today, it's not so much hard. It's more a matter of, you just have to see it. All right. Okay, any general questions before we proceed? Any general questions before we proceed? We're going to do 2-1, 2-2 today. And by the way, at about 9:10, I'll be able to start a brief homework session, and I should be able to go on after class. All right. Any questions before we go on? Any questions? All right. Keep chatting. All right. Move this over. All right. Here we go.
Hi, everyone. So where are we? First off, as far as the notes go.
Okay, let's
Hi, everyone. So where are we? First off, as far as the notes go, starting in chapter 2, we're going to go back to my older online notes. They're not as polished as chapter 0 or 1, but they're more like concise classroom notes. Actually, some students prefer these. Now, as far as the material goes, where are we? Remember that in chapter 0, we focused on mechanics, the algebraic gymnastics. In chapter 1, we talked about general function theory and general theory of graphs. Now, in chapters 2 through 4, we're going to look at particular categories of functions. Particular categories of functions. In chapter 2, we're going to look at polynomial functions and more generally, rational functions. Back in 0.6, we had this Venn diagram for function expressions. So at the center, we have these polynomial function rules, and we're going to focus mostly on these for much of chapter 2. But then we're going to talk more, in 2.6 especially, about rational expressions in general. Now, remember that all polynomial functions are rational functions. For example, we can write this polynomial as this thing over 1. The key theme of chapter 2 is polynomial and rational functions. In fact, by the end of the chapter in 2.7, we're even going to discuss the domains of these radical functions. So we're going to creep into more general algebraic expressions by the end of the chapter. And then later on, in chapter 3, we're going to discuss exponential and log functions. Those are called transcendental functions. They're beyond the algebraic. And in chapter 4, we're going to talk about trig and inverse trig functions, our old friends. So again, in chapter 2, we're going to focus heavily on these guys, and then these guys, and a little bit of these guys. Their domains. Chapter 3 with this and the log guys. Chapter 4 with these guys. Okay, so let's proceed through this Venn diagram. these various categories of functions.
All right, any questions before we go on? Any questions? Let's start chapter 2.
Chapter 1, all applied. Hi, everyone. In chapter 2, we're going to focus on polynomial functions and then rational functions more generally. Now, a particular type of polynomial function is a quadratic function. Remember, a quadratic function corresponds to a second-degree polynomial rule, such as this. And we're going to graph quadratic functions in chapter 2 as vertical parabolas. In chapter 2, we're going to graph only vertical parabolas, meaning that they either open upward or open downward. And there's a vertical axis of symmetry. So in chapter 2, we're only going to see vertical parabolas with vertical axes of symmetry. In chapter 7, we will look a little bit at these sideways parabolas, where we may have x as a function of y, but not vice versa. And in Calculus 2, Math 151 at Mesa, we're going to look, well, you're going to look at parabolas that are rotated at a 45-degree angle and such. That's for much later. But again, in chapter 2, we're going to focus on these vertical parabolas with these vertical axes of symmetry. So how do you graph these vertical parabolas in the xy plane? Well, you're going to graph something of the form y, or f of x, equals ax squared plus bx plus c. It's potentially a QT, a quadratic trinomial, although b and c could be 0. A, however, cannot be 0. If a is 0, you get a line. You don't get a quadratic, and you're not going to get a parabola. And we assume that these coefficients a, b, and c are all real numbers. Again, b and c could be 0, but a cannot be 0. The leading coefficient is especially important because it tells us whether the parabola opens upward, if the leading coefficient a is positive, or if the parabola opens downward, if the leading coefficient a is negative. So for example, on the left, we have the graph of y equals x squared minus 4x plus 5. Notice that the implied leading coefficient a is 1, which is a positive real number. The graph of that is over here on the left. So every parabola is going to have a turning point called a vertex. A parabola only has one vertex. In this case, the vertex is a local or relative minimum point because it's at the bottom of some valley. And in fact, it's the absolute minimum point for this parabola. It is the lowest point on the entire graph. There is no point with a lower y coordinate on the graph than this one. So this may be good news for cost, bad news for profit. The axis of symmetry is the vertical line that goes through the vertex. And this property of symmetry will be helpful when we graph parabolas. Remember, the idea of symmetry is that the left half of this parabola and the right half of this parabola are mirror images of each other about this axis. Now, likewise, if we have y equals the opposite of x squared plus 4x minus 3, we have a QT over here. It doesn't have to be a trinomial, but it is a quadratic trinomial. The leading coefficient a is -1, which is a negative real number. The graph of that is on the right. Now, because the leading coefficient a is negative, the parabola is opening downward. The turning point, the vertex, is the absolute maximum point on the entire graph. There is no point on the graph that's higher than this point. Once again, the axis of symmetry is the vertical line that passes through the vertex, and we have symmetry. So how do we find this magical point, this vertex? And unlike the center of a circle, the vertex of a parabola is actually a point on the graph. And we really want to know where it is. How can we find this vertex? There are at least a couple of ways of doing this, as we'll see.
Okay, any questions so far? Any questions so far? We're going to find the vertex. All right.
Hi, everyone. Let's play with Desmos. Let's enter y equals ax squared. Remember, you need the shift 6 for exponent and then the right arrow to move out, plus bx plus c. And let's put in all three sliders for the parameters a, b, and c. If you vary a, that affects the shape. If a is negative, then it opens downward. If a is 0, then you get a line. You can vary b. And you can vary c. And notice that c only affects vertical shifting. We're going to make note of that. All right, now again, what's the most important point on the parabola? The turning point, the vertex. Where is it? So what's a recipe for finding the vertex of a parabola and the axis of symmetry? We'll look at an alternate method later on. The vertex of the parabola with equation y equals ax squared plus bx plus c, where a is non-zero, is given by the ordered pair h comma k. This is pretty standard notation. Where the x-coordinate, or h, is given by this formula, the opposite of b over 2a. Does that sound familiar? The opposite of b over 2a. That's a piece of the quadratic formula, the QF. And there's a reason why, as we'll see. The y-coordinate, or k, is given by the corresponding function value. And that makes sense. Y-coordinates are function values. The idea is that if I give you y equals f of x, given an x-coordinate, if we know the x-coordinate of the vertex, then we can plug into the given function rule to find the corresponding y-coordinate. Here it should be 1. Function values are y-coordinates. So here, this is the point h comma k. Here h equals 2. We plug in the x-coordinate, h or 2, to get the y-coordinate, which is k or 1, the function value. Function values are y-coordinates. The axis of symmetry is the vertical line containing the vertex. So it has equation x equals h. Instead of memorizing that, look at this picture. Well, if the vertex here has x-coordinate 2, the vertical line here has equation x equals a number. Well, that common number better be 2. The graph of an equation consists of all points whose coordinates satisfy the equation. The x-coordinate of every point on here is 2, including the vertex. Example. Consider the parabola given by y equals x squared minus 6x plus 5. Find the vertex and find the axis or axis of symmetry. So to find the vertex, let's use this QF type formula. The x-coordinate or h, is given by this formula, the opposite of b over 2a. It might be helpful to indicate the various parameters. What are a, b, and c? A is positive 1. There's an implied 1 over here. B is, careful, B is what? B is negative 6. Watch your sign. Watch your sign. And by the way, C is 5, but this formula doesn't care. Remember, when we just see, that does not affect the x-coordinate of the vertex. It only affects the vertical shifting. So this formula for the x-coordinate of the vertex, h, doesn't even care what c is. It's only dependent on a and on b. And notice that a cannot be 0. Remember, if a is 0, we get a line. Okay, so what's the opposite of b over 2a? It's the opposite of negative 6, not positive 6, over 2 times, and then a is 1. It's a double division. You divide by both. We end up with positive 3. So positive 3 is the x-coordinate of the vertex, h. What do we do to find the y-coordinate? Y-coordinates are what? Y-coordinates are function values. You work out f of 3. The y-coordinate, k. If it helps, you can think of y as being the k here, y as being k here, and x is h over here. The y-coordinate, k, is given by the function value at x equals 3. You plug in, you substitute into this thing over here. So we get 3 squared minus 6 times 3 plus 5. This time the 5 does matter. Of course, vertical shifting does affect the y-coordinate of the vertex, right? And we get negative 4. The y-coordinate, or k, is given by negative 4. Now remember, you have to write your final answer as an ordered pair. The vertex is given by the ordered pair 3, comma, negative 4. And the axis is given by what equation? It's a vertical line. It's given by x equals 3. The same x-coordinate as the vertex. The axis, or axis of symmetry, has equation x equals 3. And in fact, and by the way, here's another important piece of information. A is positive 1. What does that tell us about the parabola? It opens upward. It opens upward. In fact, it has the same basic shape as y equals x squared. And in fact, make sure it passes the VLT. In fact, this might be all we need to know about the parabola. The fact that it opens upward, the vertex is at 3, comma, negative 4, and the axis of symmetry is at x equals 3. That might be all we need to know about this parabola for all practical purposes. But if we wanted to do a better job of graphing this thing, what are some other points we might want to find? What are some other interesting points on the parabola, and maybe some other not so interesting points? And what property will help us find points on the parabola? Hint, hint.
All right, any questions before we go on? We're going to get more points on the parabola. Refine the graph.
Next time. Hi, everyone. Let's refine the graph of y equals x squared minus 6x plus 5, our old friend. We saw where the vertex was, and we saw that it opened upward. But aside from the vertex, what are some other interesting points we might want to find? What's true for any graph in the xy plane? What points might we want to find? We might want to find the intercepts. And which intercept is normally easier to find? Y-intercept or x-intercepts? I'd say the y-intercept. Because what do you do to find a y-intercept? You set what equal to what? You set x equal to 0. You plug in 0 for x, and you evaluate f of 0. And what happens when you plug in 0 into the right side? It's an easy evaluation. What happens? These terms drop out, and you're left with the constant term, 5. F of 0 is 5, which means that the y-intercept is at the ordered pair 0, 5. Back in my day, we were lazy. We just said 5. You should say the ordered pair 0, 5. In general, if you have y equals ax squared plus bx plus c, then 0, c, where c is the constant term, that's going to be the y-intercept. Just as if you have slope-intercept form for a line. What was slope-intercept form for a line? It was y equals mx plus b. And once again, the constant term basically gave us the y-intercept, 0, b. Let's do a demonstration. Let's graph y equals x squared minus 6x. Here's y equals x squared minus 6x. It passes through the origin as the y-intercept. If we go y equals x squared minus 6x plus 5, moves it up 5 units. The y-intercept is now at 0, 5 on the blue graph. Now, how many y-intercepts can something like this have? How many y-intercepts can it have? It has to be exactly 1. There has to be a y-intercept because 0 is in the domain. There's going to be a point. But can we have 2 different y-intercepts? Is that possible? The answer is no, because then you're going to fail what test? The VLT. So this can't happen. There has to be exactly 1 y-intercept. However, think about x-intercepts. How many x-intercepts could a parabola have, a vertical parabola? Think about it. Well, you could have no x-intercepts, like a flying parabola. You could have 1 x-intercept. It bounces off the x-axis. The vertex is on the x-axis. Or you could have 2 distinct x-intercepts. And it turns out this guy will have 2 distinct x-intercepts. Find the x-intercepts, if any. Remember, there could be none. We could be in this case. We could have 1 or 2 also. How do we find x-intercepts? We plug in y equals 0. Or the function guy equal to 0. But wait a minute, that's harder. Why is it harder? Imagine plugging in 0 for y and solving for x. Why is that harder? It's harder because you have to solve an actual equation. You have to solve y, or f of x, equals 0 for the real solutions of x. Remember, only take real solutions. Only real zeros for the f function will correspond to the x-intercepts. Real zeros correspond to x-intercepts. Remember that from 1.2. So what are the real zeros of x squared minus 6x plus 5? One way to do it is to apply what formula? The quadratic formula, the QF, which we'll mention later. But it turns out that this QD can be factored nicely. How do we factor it? Remember, we're setting y or f of x equal to 0 to find the x-intercepts. We can factor this QD, and it turns out to be the factor x minus 5 times the factor x minus 1, or vice versa. The zeros are therefore 5 and 1. Which means that the x-intercepts are going to be at the ordered pair, 1, 0. Remember, they should be ordered pairs. And the numbers here are x-coordinates. Also, we have an x-intercept at 5, 0. So we're going to have here 2 x-intercepts. Now, we're in this case over here. We have 2 x-intercepts. But can you give for me an example where we're going to have no x-intercepts? What's an example of a graph that's going to look more like that? And I'll give you a hint. Can you think of an expression in x that has no real zeros? No real zeros. Here's a hint. Here's y equals x squared. It has 1, 0 at x equals 0. In fact, that's an example of the 1 x-intercept case. Y equals x squared. That has exactly 1 x-intercept. But what could you do to the parabola to make sure it has no x-intercepts? You could, for example, add 1. Notice there are no x-intercepts. And why is that? Because x squared plus 1 has no real zeros. There are no real values for x that will make this whole thing equal to 0. I doesn't count. All right. So we found the x-intercepts. We mentioned the example y equals x squared plus 1 that has no real zeros and therefore no x-intercepts, right? Let's verify what we have so far. Okay, so y equals x squared minus 6x plus 5. Let's look ahead. Let's ask Desmos. So what is y equals x squared minus 6x plus 5? Okay, remember we got the vertex from before. We got the vertex at 3, -4. That's what we have so far, right? It's the turning point. The parabola opens upward. We have the y-intercept at 0, 5 up there. And we have two x-intercepts at 1, 0, and at 5, 0. By the way, don't be spoiled. We're not always dealing with integers, but here, all these coordinates are integers.
I think I made a mistake, so I had to cut the video. Any questions so far? Any questions so far? All right, moving on. Feel free to chat or question to pause.
Hi, everyone. So far, we have 4 key points on the graph. The vertex, or turning point, 3, -4. We have the x-intercepts at 1, 0, and at 5, 0. And we have the y-intercept at 0, 5. By the way, from 0, 5, can you see how we can get a 5th point for free by using what principle? The S word. I'll give you a hint. Here's x equals 3. That's the axis of what? It's the axis of symmetry. 0, 5 is 3 units to the left of that purple axis. Notice that if we walk 3 units further to the right, 6, 5 will also be on the parabola. And we get that 5th point for free by symmetry. On top of that, you can do some more point plotting. For example, if you plug in x equals 2, it turns out that 2, -3 is also a point on the graph. Therefore, by symmetry, 4, -3 is also a point on the graph. So you can do a bunch of point plotting. Again, we're lucky because these were all integer coordinates. But even without those 2 last points, with these 5 points alone, we can get a very good sense of what this parabola looks like. I'll erase the axis even. Well, let's keep the axis in, actually. So you should be able to do a good freehand graph of the parabola. And you would probably get something like that. Very good. Now, speaking of symmetry, I'd like to talk now about the 2 x-intercepts over here, the 1, 0 and the 5, 0. I'd like to talk about these 2 x-intercepts. Notice that the axis of symmetry is right in the middle between these 2 x-intercepts. And what special point lies on the axis? The vertex. Notice that the x-coordinate of the vertex, 3, the x-coordinate of the vertex, 3, which is the x-coordinate for this axis, is the average of the x-coordinates for the 2 x-intercepts, 1 and 5. 3 is the average of 1 and 5, and that's not a coincidence. Why is it that the x-coordinate of the parabola, h, why is it given by this formula, the opposite of b over 2a?
The vertex.
Well, that came from what special formula? The quadratic formula. Right. The zeros of the function are given by the quadratic formula, the QF. Now notice that if you take a look at this formula, there are 2 cases, a plus case and a minus case. Let's go back to the parabola over here. Now, when we found the 2 x-intercepts, what did we do? We set the function rule equal to 0. We did that up here. We set the function rule equal to 0. Now, up here we used factoring, but another way we could have done it is to use the QF, the quadratic formula. We could have used the QF to solve this equation for x, and we would have gotten x equals 5 and also x equals 1. So the deal is that the quadratic formula gives us 2 cases, a plus case and a minus case. One case would give us 1, the other case would give us 5. What's the average of 1 and 5? It is 3, the x-coordinate of the vertex. What's the average of these 2 results, the plus case and the minus case from the QF? The average case is given by the opposite of b over 2a. Basically, to get the average of the plus case and the minus case, you destroy this piece of the quadratic formula. So the average of the plus case and the minus case is given by the opposite of b over 2a, just as the average of 1 and 5, the zeros of the function, that average is given by 3. So visually, it makes sense that the x-coordinate of the vertex, which is 3 here, I'll do this in purple, the x-coordinate of the vertex, which is 3 here, is given by the average of the numbers corresponding to the x-intercepts, 1 and 5. That's because the opposite of b over 2a is the average of the plus case and the minus case from the QF. Now, if there's just one x-intercept, well, great. The vertex is the x-intercept. So the discriminant is 0, right? And this part would drop off anyway. So the opposite of b over 2a, that would give the x-intercept and the x-coordinate of the vertex, h. But the funny thing is that even for a flying parabola, it turns out that the opposite of b over 2a will give the x-coordinate of the vertex even in that case, although it's not as easy to visualize why that's the case. But at this point, you should see why it makes sense that the opposite of b over 2a is the formula for h, the x-coordinate of the vertex, is the average of the x-intercepts if they're real. But see, it's the case even if they're not real. All right. Next up, what is another way that we can find the vertex?
All right, so any questions so far? Any questions so far? We're going to play with Desmos also. Any questions? Feel free to chat.
Hi, everyone. Let's have Desmos experiment with this cutie form for the equation of a parabola. Y equals ax squared plus bx plus c, the descending powers form for the equation of a parabola. Now, if we vary a, we're varying the shape of the parabola. Notice that as a stays positive and increases, it gets steeper and steeper. If a is 0, then we get a line. That's not a parabola. If a is negative, it opens downward. But as we move away from 0, again, the parabola gets steeper and steeper. If we vary b, then we're getting both horizontal and vertical shifting, but we are retaining the shape of the parabola. The shape of the parabola is entirely determined by a and its orientation. But b can affect horizontal and vertical shifting, and c can affect vertical shifting. But bear in mind that both b and c affect vertical shifting. So a is very meaningful. It gives you the shape of the parabola and its orientation. But b and c, their impact is less clear. So although a is very meaningful, b and c are not as meaningful. Although it is true that there is an important application of c. Let's say c equals 4, for example. What does c tell us? It tells us where what point is. Y-intercept. But when you look at the descending powers form for the equation of a parabola here, a is very meaningful. It gives you shape and orientation. B is hard to interpret. And C, the direct purpose of C is to give us the y-intercept. But otherwise, B and C work in concert to give us the shifts. So generally speaking, the parameters A, B, and C are a mixed bag in terms of their meaningfulness. So we might want a form where the parameters are more meaningful. And that's for next time.
Right. Any questions there? You might want to play with Desmos. This is really fun. Any questions?
Hi, everyone. How can we get a more meaningful form for the equation of a parabola in the xy plane? Let's start with y equals ax squared. If a is positive, the parabola opens upward. If a is 0, we get a line. That's not a parabola. If a is negative, the parabola opens downward. But as we vary a over all non-zero real values, we get all possible shapes of the parabola and both possible orientations, opening upward or downward. So we get all possible shapes and both possible orientations of all vertical parabolas in the xy plane. But what if we want to allow for horizontal shifts by h units? We would then substitute x with what? Remember section 1.4. To get a horizontal shift by h units, we would substitute x with the quantity x minus h. So now, as we slide the value of h, that leads to horizontal shifting. So for example, if h equals 2, the vertex is at 2, 0. But what if we want vertical shifting? What do we do? If we want a vertical shift by k units, what do? We tack on a plus k, and then we get our vertical shift. If k equals 1, our vertex is at 2, 1. K affects vertical shifting. So, together, by changing a and h and k, by varying these various values for these three parameters, we get all possible vertical parabolas in the xy plane. This is called vertex form or standard form. The standard form or vertex form for the equation of a parabola. It's given by y equals a times the square of x minus h all plus k. Now, when students write this out, they often forget the square. So when you write this out, you might want to write it as y equals a times the square of x minus h. Because students are so proud of the fact that they write x minus h that they then forget the square. Don't forget the square. All that plus k. Don't engage in wishful thinking. It's linear. It's not linear, it's quadratic. Vertex form. So this parabola has the same shape as y equals ax squared, but the vertex is at the point h, k. The vertex for y equals ax squared has to be at the origin, 0, 0. But in general, for this form over here, the vertex is at the point h, k. Basically, we have translated or moved or shifted the vertex and therefore the parabola, h units horizontally and k units vertically. Now, you can use your algebraic magic and rewrite this in descending powers form. Y equals ax squared plus bx plus c. But perhaps the one advantage to this is the fact that c gives you what point? The y-intercept, which is not as clear from the vertex form. But otherwise, the vertex form is much more meaningful. A is meaningful in terms of shape and orientation. H and k give you the vertex, so these parameters are very meaningful. And by the way, do observe that the a in the vertex form here and the a over here in descending powers form, these are the same value. These are both the leading coefficient. They're both a coefficient on x squared in the end. So the a here is the same as the a here. So they have the same meaning. The leading coefficients are the same. Next, let's do an example on how to convert from descending powers form to vertex form.
Okay, any questions? Any questions? It's a matter of seeing this bit by bit. Any questions?
Hi, everyone. Let's convert from this descending powers form for the equation of a parabola, y equals 3x squared plus 12x plus 11, into this standard or vertex form, y equals a times the square of x minus h all plus k. Don't forget the square. And we'll find the vertex. Now, look at this. We'd like to get here the square of a binomial. And when I see something like the square of a binomial, I'm thinking CTS. What does CTS stand for? completing the square. That process that we saw with equations of circles back in 0.13. Remember circles in 0.13. So what we're going to do is we're going to group the x squared and the x terms, and we're going to factor out a, which is 3 here. That's going to be our first step. Again, group the quadratic and linear terms. We're going to group together the 3x squared plus 12x, and we're going to separate out the plus 11. It's on its own. And then we're going to factor out a from this group. A equals 3, we factor out 3 from this group, but not the 11. When you divide, when you factor out the 3, you get 3 times the quantity, x squared plus 4x, and you have all of this plus 11. And don't forget the y equals over here. Now bear in mind, you factor out a. You don't factor out the GCF. For example, we don't factor out the x. Also, what if we had had 3x squared plus 11x or 13x? You would still factor out the 3, in which case, instead of a 4, you might be getting 11/3 or something like that. And that's okay. You might get fractions. Don't be afraid of fractions. I was being nice here. When you divide 12 by 3, you get 4. I was being nice. Remember, you factor out a, that leading coefficient. If you end up with something like 11/3, too bad. You end up with 11/3. Okay, now we're going to CTS, complete the square, and compensate. We have to pay for how we change the right-hand side. First of all, let's CTS. Let's complete the square. All right, so we take this coefficient on x, 4. It doesn't matter if it's positive or negative, but it is a positive 4. What do we do? Well, we take 4, and when we take half of 4, we get 2. Half of 4 is 2. And then what do? We square the 2. When we square the 2, we get 4 again, actually. So that means that in order to complete the square, we have to put a plus 4 inside the parentheses here, so that we end up with a PST. Remember, the goal is to make this thing a PST, a perfect square trinomial, so that it can be factored like this thing, the square of a binomial over here. But now wait a minute. We also have to compensate. We have to pay for what we do over here. We can't just throw in a plus 4 because we feel like it. And you have to be careful. How do we pay for inserting a plus 4 inside the parentheses here? A naive student might say, oh, well, I guess we subtract 4. Which I would understand, but you're being a bit naive. Because here's the problem. When we insert a plus 4 here, notice that there's a 3 out in front. Before, when we dealt with circles, we made sure that the leading coefficient was 1. We don't have that guarantee now. A equals 3 here, and guess what? The 3 impacts the 4. If you insert a plus 4 inside the parentheses, what are you really adding to the right-hand side? Not just 4, but 3 times 4. So when you insert the 4 in there, remember, you're adding 3 times 4. You're really adding 3 times 4 by the distributive property. When you insert the plus 4, you're really adding 3 times 4. You're adding 3 times 4. And how do you pay for adding 3 times 4 or 12? You subtract the 3 times 4 or 12. But don't forget, the 4 is getting hit by the 3, so you have to take that into account. It's a very common error to forget that. So to compensate for this, you have to subtract not 4, but 12. You can put 12 here. So next, since we should have a PST here by now, we need to factor the PST so that it looks more like this, the square of a binomial. How do you factor this PST? X squared plus 4x plus 4? Well, it is the square of x, now that middle sign matters, plus 2. Basically half of that coefficient on x. So we get the square of x plus 2 over here. Over here, 11 minus 12 gets us a negative 1. All right. So we do the factoring. When we factor the perfect square trinomial, we get y equals 3 times the square of x plus 2, all minus 1. Right. Just for kicks, let's see if we got the right answer on Desmos. Y equals 3 times x plus 2, x plus 2 all squared minus 1. All right, so I claim that the given equation graphs as that. What was the given equation? It was y equals 3x squared plus 12x plus 11. Y equals 3x squared plus 12x plus 11. Yes, they overlap. This is a graphical demonstration of equivalence. So it looks like we've gotten the right answer here. It's not a proof, but it's pretty convincing. All right. Oh, and by the way, where is the vertex? Where's the vertex? What is h, the x-coordinate of the vertex? Remember, be careful. Because remember, it's the square of x minus h. X plus 2 is x minus what? It's x minus negative 2. And all that's getting squared. So h is actually negative 2. Okay? You actually have to flip the sign. Remember, the sign is surprising. X plus 2, you might think you're moving right by 2 units. No, no, no. Remember, sign surprise when it comes to horizontal shifting. Horizontal shifting, the signs surprise. H is negative 2, not positive 2. You're doing a shift left by 2 units. K, however, you just grab the negative 1. You're moving down 1 unit. The vertical shift is very straightforward. So the new vertex will be at negative 2, comma, negative 1. Remember, there is a sign flip from here to here to get the x-coordinate, h, but there is no sign flip for k, the y-coordinate. So watch out. Again, here on the graph, you can see negative 2, comma, negative 1 is in fact the vertex. Now, what's a way of seeing that x equals negative 2 leads to the vertex? In fact, one way to look at it is that x equals negative 2 makes this equal to 0. Remember that trick with the equation of a circle? Remember that the center of the circle, h comma k, made the left-hand side equal to 0. It made both of these square guys equal to 0. Similarly, you want the value for x, or h, that will make this square thing equal to 0. And why is that? Well, remember, when you look at this vertex here, right? The vertex here is the most extreme point on the parabola. In this case, it's the absolute minimum point. It's the most extreme point on the parabola. It's the lowest point. Well, look at this square thing here. What is this square thing at its most extreme? What is the most extreme value of a square? You could say it's 0, because if you keep it real, squares are never negative. Squares are never negative. The most extreme this can be is 0. Okay. The vertex is the most extreme point on the parabola. Notice that 0 is the most extreme a square can get. So it makes sense that the value for x that makes this square thing equal to 0 leads to the extreme point on the parabola, because 0 is the most extreme value for this squared expression. So the axis of symmetry is x equals negative 2. Remember, it's the vertical line that goes through the vertex. X equals negative 2, h over here. And a equals 3, that's positive. We know the parabola opens upward. A equals 3, which is positive, the parabola opens upward. Next up, we're going to do some modeling. Given some points, find the parabola passing through them.
Any questions before we do this more mechanical problem? Any questions? Any questions? It's all pretty cool. Just take it step by step.
Hi, everyone. Back in section 0.14, we talked about a classic problem with lines. Given two distinct points in the xy plane, find an equation for the line containing those points. Now, how many distinct points in the plane will determine a vertical parabola? 3. So, given 3 distinct points, find the equation of the parabola, the vertical parabola, that connects the 3 points. Now, bear in mind, the 3 points have to be non-collinear. Not only do they have to be distinct, they have to be non-collinear, meaning that they cannot lie on a straight line. There's no way that these 3 points will determine a parabola. Now, for the general problem involving 3 non-collinear points in the plane, you may have to solve a system of 3 linear equations in 3 unknowns using matrices, perhaps. That's chapter 8. But it would be very convenient if one of these 3 points were known to be the what of the parabola. If one of these 3 points were known to be the vertex of the parabola, V. In which case, in order to determine a vertical parabola, we just need one other point in addition to the vertex. Because remember, since there's an axis of symmetry, there's an implicit third point over here that's given for free. So if we know the vertex and one other point on the parabola, then again, we can get a third point by exploiting symmetry, but we don't even need that third point when we do the calculations. Instead of going through some complicated thing with descending powers form, instead of having to deal with matrices, we can deal with the vertex form. Y equals a times the square of x minus h plus k. Once again, what do students forget? They often forget the square. They forget it's a quadratic, in part because they're so proud when they write x minus h in parentheses, they forget the square. Don't forget the square. Example, find an equation for the parabola, the vertical parabola, that has vertex 4, 2, and that contains the point 1, 29. So if you go to Desmos, all right, well, we're claiming that we need a parabola with vertex 4, 2, all right, 4, 2, that's right there. Now, we want this parabola to go through the point 1, 29. I don't see 29 in this y-axis, so I think we're going to need unequal axes in this case. So let's go to the wrench over here in the upper right. For y-axis, instead of from about -8 to +8, why don't we go from about -10 to +40, let's say. If you want, you could change the step size and have things where the tick marks are by 5s, the number tick marks, but we can stay by 10 for now. All right. We can add labels also, put y here and x here. We really should do that, actually. Label the axes. We really should do that. Okay. So where's the point 1, 29? Right there. I want the vertical parabola that has 4, 2 as the vertex, and that passes through 1, 29. This parabola is going to open how? Well, it's got to open up if it's a vertical parabola. So let's find the parabola that connects these dots with 4, 2 as the vertex. Okay, so here's vertex form. Well, I'm telling you what the vertex is 4, 2. H equals 4, k equals 2. So you can plug these in for h and k. So h equals 4. We still have the minus sign in front. K equals 2. So we have y equals a times the square of x minus 4, all plus 2. Now, we have values for 2 of the 3 unknown parameters, h and k. We now need to know the value for a. So how can we solve for a? There's another piece of information we can use up here. the fact that the point 1, 29 has to lie in the parabola. Remember the basic principle of graphing. The graph of an equation consists of all points whose coordinates satisfy the equation. So in order for this point to be on the parabola, x equals 1 and y equals 29 must satisfy this equation. Let's plug those values in. Plug in x equals 1, plug in y equals 29, right? And we get this over here. X equals 1, y equals 29. And now we can solve for a. 1 minus 4 is negative 3. The square of negative 3 is 9. So we get 29 equals 9a plus 2. If you had forgotten the square, you'd have had negative 3a. Don't forget the square. Okay, let's subtract 2 from both sides. We get 27 equals 9a. So a is what? Dividing both sides by 9, a equals 3. Again, a does not have to be integer, but here it is. We're not done yet. What do we have to do? We have to take this value for a, and just like with y equals mx plus b, just like with those variation problems from 0.16, you have to plug this in. Back to here. Remember, we now know h, we now know k, and now we know a. We can plug in 3 for a. And then from here, we get our final equation in vertex form. Y equals, remember, a equals 3 times the square of, don't forget the square, the square of x minus 4, all that plus 2. Well, let's see if this works. Y equals 3 times x minus 4 all squared, all that plus 2. Yes, it does. Notice that 4, 2 is the vertex over here, and it passes through the point 1, 29 over here. Vertex of 4, 2 goes through 129. I guess it's good to flash the labels. And of course, it opens upward. A equals 3, which is positive. Very good. So we've done our modeling problem. All right, after this, what happens if we go beyond quadratics and parabolas?
All right. So actually, it might be a good time for a break because remember, we're going to have a question session and that's part of the class. It's 8:03 now. Let's come back at 8:14. So break until 8:14, and then we'll do section 2.2. All right. So please mute. Okay. Break until 8:14. Please mute. And I got to remember to record. I'll pause now. By the way, any questions? Any questions? Right? Okay. Pause. Okay, so I have 8:14. Any questions about parabolas from 2.1, quadratics, graphing quadratics, before we move on to higher degrees? Any questions? Any questions? Okay, feel free to chat. All right. And let's get started. Okay, I think it's the previous video here.
Hi, everyone. In section 2.2, we'll look at graphs of polynomials of degree 3, 4, and so forth. We'll discuss ideas of infinity and limits in our examples. Let's go straight to bowls and snakes. In the long run, non-constant polynomial graphs will look like bowls or snakes. So let's get straight to Desmos. Let's look at y equals ax squared. These are parabolas. If a is positive, they open up. If a is negative, they open down. Let's now look at y equals bx to the fourth. Again, these are bowls. They're not technically parabolas, but they're bowls. If the coefficient is positive, they open up. If the coefficient is negative, they open down. Notice that compared to the parabolas, these ax squared guys, notice that these green graphs, y equals bx to the fourth, they're steeper far away from x equals 0, but close to x equals 0, if you zoom in, actually the green graph is flatter than the red graph. So notice that the higher the degree is, the flatter the graph is close to the origin. Far away from the origin, the green graph's actually steeper. And so forth. Y equals cx to the sixth. Again, bowls opening up or down. Flat, very flat, near the origin. For example, 1/2 to the sixth is very close to 0. So the graphs for y equals ax to the second, fourth, sixth, and so forth, where the exponents here are even and positive, the graphs of these are bowls. If a is positive, they open up. If a is negative, they open down. So for example, on the left, we have the graph of y equals x squared, f of x equals x squared. It's a bowl opening up. On the right, we have the graph of y equals the opposite of x squared. G of x equals the opposite of x squared. That's a bowl opening down. Now, in the homework, you're expected to be able to evaluate these kinds of long-run limits. Long-run limits. The limit of f of x as x approaches either infinity or negative infinity. Basically, when you're asked to evaluate a long-run limit, evaluating a long-run limit, then you're basically being asked the question, what are the y coordinates approaching on the graph as x approaches either infinity or negative infinity? That is, as we look towards the right forever and ever, in the case where x is approaching infinity, or in the case where we look left forever and ever, as x approaches negative infinity. We're asking, what is the y coordinate approaching in the long run as we look off to the right and as we look off to the left? These are what I call long run limits. And for these bowls and snakes, the answers to these limit questions will be either infinity or negative infinity, if you're dealing with these kinds of polynomial bowls or snakes. Okay. So in the case of y equals x squared, f of x equals x squared, as x approaches infinity, well, as x goes off to a million, a billion, a trillion, what's happening to the y coordinates? The y coordinates are also approaching infinity. So the limit of f of x as x approaches infinity will be infinity. As we look off to the right, as x approaches infinity, the y coordinates also approach infinity. They increase without bound. Likewise, what's happening as x approaches negative infinity? What happens as x goes off to negative a million, negative a billion, and so forth? Well, as x approaches negative infinity, still the y coordinates approach infinity. This is because of symmetry. So in both cases, the long run limits will be infinity. Now, the phrase, go back to where you came from, is often taken as rude, but here it's very appropriate. If you look at things left to right, what's happening with this bowl? This bowl is coming down from infinity, is coming down from the heavens, and then over here to the right, it's going off towards infinity. It's returning to the heavens. So it's going back to where it came from as you look from left to right. And bowls have that property. Look at the graph of y equals the opposite of x squared, this g function. This time, as x approaches infinity, as we look off towards the right, the y coordinates are decreasing without bound. The function values are decreasing, negative a million, negative a billion, and so forth, towards negative infinity. As x approaches infinity, the y coordinates, the g of x values, approach negative infinity. Likewise, as x approaches negative infinity, as we look off towards the left forever and ever, the y-coordinates, the function values, are also approaching negative infinity. So again, these two match up. Bulls have that property where the two long-run limits will be the same. They'll either be both positive infinity or both negative infinity. Again, if we look from left to right, we're going back to where we came from. We're coming up from down below, like hell, I guess. And then as we look left to right, we're returning to hell. We're going back to hell. We're coming up from hell, and we're going down to hell. All right. And both have that property. Now, what about the graphs of y equals ax cubed and so forth? Let's take a look here. So y equals ax cubed. Okay, so that's going to be a snake here, right? If a is positive, we get a rising snake. If a is 0, that doesn't count. That's the flat line, y equals 0. If a is negative, we get a falling snake. Likewise, y equals ax to the 5th. Sorry, bx to the 5th. If b is positive, it's a rising snake. If b is negative, it's a falling snake. Again, similar to the situation with fourth degree versus second degree before the bulls, the higher the degree, notice we're steeper far away from the origin, or x equals 0, out here and out here, but we're very flat. The green graph is flatter than the red graph as we get close to the origin. Similarly for y equals cx to the 7th. Rising snakes and falling snakes, steep far away from the origin, but very flat close to the origin. So here we have our snakes. On the left, we have the graph of y equals x cubed, the f function. On the right, we have the graph of y equals the opposite of x cubed, the g function. Now, answer the same questions that we asked before. What are the long-run limits? I'll do this. So what is the limit of f of x as x approaches infinity? And as x approaches negative infinity? What's the limit of g of x as x approaches infinity and as x approaches negative infinity? What will be your answers here? Remember, the answer to these, when you're evaluating these long-run limits, you're answering the question, what are the y-coordinates approaching? And the answer to each of these will be either infinity or negative infinity. All right. So notice that with these snakes, you're running away from where you came from. So notice as you look from left to right, okay, you're coming up from hell, but then you're going up to heaven. Likewise, over here from left to right, you're coming down from heaven, and then you keep going down to hell. All right. So in the case of y equals x cubed, as x approaches infinity, the y-coordinates also approach infinity. So as x goes to a million, a billion, a trillion, the y-coordinates are going a million cubed, a billion cubed, a trillion cubed, and those are also approaching infinity. So that long-run limit will be infinity. As x approaches infinity, this long-run limit will be infinity. As you look to the left, negative a million, negative a billion, then you're talking about negative a million all cubed, negative a billion all cubed. Again, you're approaching negative infinity. So as x approaches negative infinity, the y coordinates also approach negative infinity. Notice that these are different answers. So to these long-run limit questions, you're getting different answers. One's infinity, one's negative infinity. In the g case, it's switched. As x approaches positive infinity, g approaches negative infinity. And as x approaches negative infinity, g approaches positive infinity. But again, for these bowl and snake graphs, for polynomial functions, in the long run, you're either going to get infinity or negative infinity for these two directions. Here, you have a mix for these snakes. One's infinity, one is infinity, the other is negative infinity for these snake cases, because you're running away. Okay, next, we're going to talk about why, when we look at polynomial graphs, non-constant polynomial graphs, in the long run, we're basically dealing with a bowl or a snake.
All right. So now is a good time. Let me see here. Yeah, whenever I think of the term bowls and snakes, I think of this clip from. Okay, and if you hate Family Guy, hate Family Guy. All right, let's go on. So in the long run, we have bowls and snakes. A lot of this is bowls and snakes.
Hi, everyone. Let's consider the graph of y equals f of x, which is 4x cubed minus 5x squared minus 7x plus 2. Now, two of these terms are immediately informative. The positive 2 tells us what? It tells us that the y-intercept for this graph will be at the point 0, 2. Because when you plug in x equals 0, these go bye-bye, and you're left with a constant term, 2. But more importantly, the leading or dominant term, 4x cubed, tells us a lot. This tells us what the graph basically looks like in the long run if we zoom out. Then we can figure out the long run limits for this function. That's why I call this the zoom out dominance property. The leading term basically tells us what's going on. So how do we graph y equals 4x cubed? Because the graph of y equals 4x cubed will exhibit basically the same long-term, long-run behaviors as this over here. How do you graph y equals 4x cubed? It's going to be a rising snake. As x approaches infinity, as we look to the right, the graph goes up, up, up towards infinity. Y approaches infinity. As x approaches negative infinity, as we look to the left, the graph goes down, down, down. The y coordinates or function values approach negative infinity. And the same is true for the graph we care about. Notice that the y-intercept is at 0, 2. That's what that constant term tells us. But the leading term, 4x cubed, which is the same as this, it tells us that both of these graphs will have the same long-run behavior for all practical purposes. It might be more helpful if we have unequal scales. Let's make the x-axis more like -5 to +5. And the y-axis is going from like -40 to 40. Okay, this might be a bit more informative. You can see that in the long run, right? Again, if you look at the red graph and the blue graph, the red graph and the blue graph, they both go up, up, up as x approaches infinity, and they both go down, down, down as x approaches negative infinity. They share the same long-run behaviors. Y equals x cubed is in blue here, and the graph we care about is in black. The graphs look similar in the long run. So here are the long run limits for both the 4x cubed function and also the function we care about. The limit as x approaches infinity, as we look off to the right, the y coordinates approach infinity for both graphs, Likewise, as x approaches negative infinity, the y-coordinates, the function values, approach negative infinity. As x approaches negative infinity, the y-coordinates, the function values, approach negative infinity for both 4x cubed and the function we care about. The zoom out dominance property, that's my term. The leading term of a polynomial, f of x, increasingly dominates the other terms and increasingly determines the shape of the graph in the long run as x approaches infinity or as x approaches negative infinity. So if x is close to 0, then the blue graph exhibits some lumpiness, and that's determined by these two terms in the middle. The constant term just leads to a vertical shift, but there's more of a struggle here because of these two terms in the middle, and we get some lumpiness. We get a local max point up here, and we get a local min point down here because of these two middle terms. So if x is close to 0, basically, then these lower order terms can matter. But as x moves far away from 0, as x approaches plus or minus the millions, billions, trillions, the leading term is the term that really, really matters in the long run. And these lower order terms really don't matter at all. They barely matter at all. So if x is close to 0, the lower order degree terms can put up a fight for part of the graph, and we can get some local or relative maximum and minimum points, turning points. We do get turning points up here and down here. But in the long run, the leading term dominates. By the way, in calculus, you'll locate the turning points. By the way, one side note, if you have a special case like this, where you have, say, a 4th degree polynomial that can be factored like that, then it might be better looked at as a translation problem. For example, y equals x to the 4th looks like that. Y equals x plus 1 all to the 4th. Basically exhibits the same behavior in the long run because it just corresponds to a horizontal translation. Okay, next up, let's talk more about turning points and the possible numbers of turning points for polynomials of various degrees.
Okay, any questions? We're going to talk about those local max and min points, which you deal with a lot of in calculus, actually. All right. Okay, any questions? Any questions? Okay, so I'm recording, all right. Hi,
everyone. How many turning points can a polynomial graph have? Let's take n equals 1 as the degree, first degree, n equals 2, second degree, and n equals 3, third degree. So how many turning points can a first degree polynomial graph have? A first degree polynomial means linear. How many turning points can a line have? Well, none. The graph can never turn around. 0 turning points, TPs. How do you graph a second degree polynomial? That's going to be a parabola. And how many turning points does it have? It has to have exactly 1 at the vertex. So we're going to have 1 turning point here. But now how many turning points can a third degree polynomial graph have? It depends. And in fact, we have a couple of examples here. The graph of y equals 4x cubed, that has no turning points. We say that this function is monotonically increasing. It keeps going up, 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 up. This graph has no turning points, 0 turning points. But its partner over here, which is the graph we cared about earlier, this blue graph, it has 2 turning points. It has a local or relative maximum point, a hilltop point over here, and it has a local or relative minimum point, a valley bottom point over here. The red graph has 0 turning points. The blue graph has 2 turning points. So it depends. A third degree polynomial graph could have 0 or 2 turning points. It depends. Now, in general, only very high degree polynomial graphs can have many turning points. only high-degree polynomial functions can have very wavy graphs. In particular, the graph for a non-constant nth-degree polynomial, y equals f of x, can have no more than n-1 turning points. So for example, if you have a polynomial graph with 99 turning points, then that means that the degree better be 100 or higher. Only high-degree polynomial graphs can be very wavy and have many turning points. Now let's say we have an even degree polynomial graph, and it does matter very much if the degree is even versus odd. In the long run, what does a non-constant even degree polynomial graph look like in the long run? It has to look like a bowl. In the long run, now it might be a little wavy in the middle, but in the long run, you're going to get a bowl, which means that ultimately you have to go back to where you came from. If you came down from heaven, you have to go back up to heaven. Which means that you have to have an odd number of turning points. The graph of a non-constant even degree polynomial must have an odd number of TPs. Because a bowl can turn around once, and then all future turning points have to come in pairs. If you turn around again, it has to turn around again. And then if it turns around again, it has to turn around again. So after the first turning point, all subsequent turning points have to come in pairs. So odd number of turning points. Could be 1, could be 3, could be 5, and so forth, depending on the degree.
Right. Yeah, I made a mistake, so that's why I cut it there. Questions about turning points. We're looking at the possible number of turning points for these bulls and snakes. Questions.
Hi, everyone. How do you graph odd degree polynomial functions? What do they look like in the long run? In the long run, they look like snakes. Now, if you look at the graph of y equals x cubed, or for that matter, y equals x, there are no turning points. So you don't have to have any turning points. But if you do turn around, you better turn around again. So anytime you turn around, there better be a partner turnaround point. If you turn around again, you better turn around again. These have to come in pairs. So here you could have 0 turning points, 2 turning points, 4 turning points, and so forth. The graph of an odd degree polynomial must have an even number of turning points. Notice the parities here are different. A parity means odd versus even. Oh, by the way, regarding odd degree polynomial graphs, they always have to have a real 0. Why is that? Why do odd degree polynomial functions always have to have a real 0? Because the graphs always have to have a what in the xy plane? A snake always has to have an x-intercept. An odd degree polynomial must have at least one real 0 because the graph must have at least one x-intercept. Good to know. So now, there's a handy-dandy algorithm for figuring out how many turning points you can have. Because here's what you do. Find the possible number of turning points for a non-constant polynomial graph. Here's what you do. Polynomial graph of degree n. Here's what you do. You start with, now this is to get a list of the possible number of turning points. You start with n minus 1. That's going to be the possible number, the maximum possible number of turning points. Then keep counting down by 2s and stop before you hit negative numbers, because you cannot have a negative number of turning points. So for example, let's say you have a third degree polynomial, n equals 3. Well, you start with n minus 1, which is 2. Count down by 2. 2 minus 2 is 0. So you can have 2 turning points or no turning points. And of course, you cannot have negative 2 turning points. So you stop at 0. And that makes sense, right? We saw that. The blue graph had 2 turning points. The red graph had no turning points. These were both cubics, third degree. Why does this work? Well, 3 is an odd degree. And remember, for an odd degree polynomial, you have to have an even number of turning points. Well, if n is odd, n minus 1 is guaranteed to be even. These are all guaranteed to be even. And remember our rule from up above. Remember that for a non-constant nth degree polynomial, you can have no more than n minus 1 turning points. N minus 1 is the maximum possible. So when you list out the possible numbers of turning points, you start with n minus 1, the degree minus 1, and you count down by 2s. And of course, you cannot have a negative number of turning points. Now, what about a 6th degree polynomial graph? How many turning points can a 6th degree polynomial graph have? Again, let's use the algorithm. We begin with n equals 6. That's the degree, and it's even. So we start with, to get our list of the possible numbers of turning points, we start with n minus 1, which is 6 minus 1, or 5. Notice that 5 is odd. Remember, an even degree polynomial graph has to have an odd number of turning points so that it goes back to where it comes from. Here we have 5 turning points. 1, 2, 3, 4, 5. There's some 6th degree graphs that do this. 5 is the maximum possible, and it's odd, so that's legal, and then you keep counting down. So we have 5, we start with 5, count down by 2s. 5 minus 2 is 3, 3 minus 2 is 1. And we cannot go to negative 1. We cannot have a negative number of turning points. So a 6th degree polynomial graph could have 5 or 3 or 1 turning points. It's got to turn around at least once, otherwise it can't be a bull. So 5, 3, or 1. Remember, only high degree polynomial graphs can be very wavy. Here you have 1 turning point, here you have 3. And there are others with 5. Okay, so again, start with n minus 1, the degree minus 1, count down by 2s. Stop before you reach negative numbers. That's to get the list of possible numbers of turning points. As for which case you actually have, well, take calculus. And what are you going to look for in calculus? You're going to set the derivative equal to a certain number and solve for x. What is the slope of a horizontal tangent line? Notice at these turning points, these relative max and min points, you have horizontal tangent lines. The slope of the tangent line is the derivative. You want to set the derivative equal to, what's the slope of a horizontal line? 0. Set the derivative equal to 0, solve for x. And that's going to help locate these turning points. That'll be for calculus. Okay. Next up, we're going to talk about X-intercepts.
All right, so we've been talking about turning points. Those are more for calculus, actually. X-intercepts are more pre-calc. Any questions so far? Any questions so far? Again, you tend to locate turning points more in calculus. All right.
Hi, everyone. Last time, we talked about turning points for polynomial graphs. That's where the derivative is 0. But what about where the function itself is 0? Remember that the real zeros of f of x correspond to what points on the graph? The real zeros of a function correspond to what points on the graph? Remember, f of x, think y. Where is y equal to 0? The real zeros of f of x correspond to the x-intercepts on the graph of y equals f of x. The real zeros of f of x correspond to the x-intercepts on the graph of y equals f of x. Y equals 0 at the x-intercepts. We want to find the real solutions for f of x equals 0. The x-intercepts correspond to the real solutions for f of x equals 0. X-intercepts correspond to the real solutions of f of x equals 0. All right, so the real zeros over here, over here, over here, and over here. It looks like this polynomial function has 4 distinct or different real zeros. Let's talk more about these. Zeros and the factor theorem. Now let's say that f of x is a polynomial in x, and it's not the 0 polynomial. It turns out that 2 is a 0 of this function if and only if x minus 2 is a factor of f of x. And therefore, there would be an x-intercept at 2, 0. Likewise, 3 is a 0 of f if and only if what is a factor of f of x? X minus 3, in which case, what will be an x-intercept? 3, 0. Now, negative 3 is a 0 of f if and only if what is a factor? X minus negative 3 or x plus 3. Negative 3 is a 0 of f if and only if x plus 3 is a factor of f of x, in which case we have an x-intercept at negative 3, 0. In general, if f of x is a non-zero polynomial and k is a real number, then k is a 0 of f if and only if x minus k is a factor of f of x. That's the generalization of what we talked about over here. And also, remember that with turning points, for an nth degree polynomial graph, we could have at most n minus 1 turning points. Actually, we could have as many as n real zeros or n x-intercepts. An nth degree polynomial can have at most n real zeros and therefore n x-intercepts. All right. So for example, let's find a third degree polynomial function that only has 4 and negative 1 as zeros. All right. Now, first off, because 4 is a 0 of this polynomial function, let's assume it's a polynomial in x. If 4 is a 0, then what has to be a factor? X minus 4 has to be a factor. If negative 1 is a 0, what has to be a factor? X minus negative 1 or x plus 1. Now, if we let f of x be this, will this satisfy the conditions here? Not quite, because what degree is this function here? in purple. This would be second degree, and we're looking for third degree. So what can we do to up the degree? A lot of students would attach an X over here. But there's a problem with doing that. If you attach an X here, what else would be a 0? Then 0 would also be a 0, and that's not specified as a desired 0. So it's not appropriate to just attach an X. What would be another way to up the degree such that we're not throwing in any more distinct factors? We could square one of these. We could put the square over here, or we could put the square over there. Furthermore, we can multiply by a non-zero number. We could multiply by 2, by 3, by 4, by negative 100, whatever. In general, we can multiply by a, where a is a non-zero real constant. And again, the square can either go on this factor or that factor. And in fact, when you consider all these possibilities, this will represent all possibilities for third degree polynomial functions in X that only have 4 and negative 1 as zeros. These represent all the possibilities, where a represents any non-zero real number. So anything of this form or this form, a times the square of x minus 4 times the factor x plus 1, or a times the factor x minus 4 times the square of x plus 1. These forms only differ in which factor gets the square. Now, what are some differences, by the way? So over here in blue, what's going on with this blue polynomial? All right, well, you could say we have 3 real zeros for this third degree polynomial. Their names are 4, 4 again, and negative 1. I'm listing 4 twice because the exponent here is 2. And 2 here is called the multiplicity of 4 as a 0. So for this left form here, 4 is a 0 of multiplicity 2, corresponding to the exponent. That means that 4 comes in as a 0 twice. And you can think of this as the factor x minus 4 times itself. And then negative 1 is a 0 of multiplicity 1. Negative 1 is a 0 of multiplicity 1 because the implied exponent here is just a 1. So there are 3 real zeros for this polynomial, but only 2 of them are distinct. There are only 2 distinct or different real zeros, the 4 and the negative 1. So if I just ask you to list out the real zeros, you can write them out with multiplicity. The 4 comes in twice. If I have something like x to the 10th, then 0 is a 0 10 times. 0 is a 0 of multiplicity 10. Look at that exponent. Likewise, what's happening over here? In green. Tell me about this green polynomial for any non-zero value of a. What are the real zeros? Well, same as before. There are 3 real zeros, but their names are 4, negative 1, and negative 1. This time it's the negative 1 that's repeated. And this time, 4 is a 0 of multiplicity 1, and negative 1 is a 0 of multiplicity 2. Right, corresponding to the exponents here, 1 and 2. All right. Now, why do we care? Why do we care? Because of the following principle. If you have a 0, a real 0, of odd multiplicity like 1, that means that at the x-intercept, remember, real zeros correspond to x-intercepts. That means that you get a cut there. If you have a real zero of odd multiplicity, like 1, then the x-intercept there has the graph cutting. The graph of y equals f of x cuts at that corresponding x-intercept. And I'll show you what I mean by a cut. Okay. Likewise, if you have a real zero of even multiplicity, like 2 or 4 or 6, then the graph of y equals f of x bounces at that x-intercept. Basically, if you have odd multiplicity, the graph acts like a snake around that x-intercept. If the multiplicity is even, the graph acts like a bull, and you bounce. So it's kind of like snake versus bull. All right, so let's take a look at these graphs. And if you want, you could expand them out. What do these graphs look like? All right. If I take the first case, the blue case, where a equals 1. If a is 2 or 3, that's just a stretching. Let's take a look. Now, as we look left to right, if we expand this out, the leading term is going to be x cubed. You could judge that from here as well. But you can tell even from here that the leading term is going to end up being x cubed, which means that overall, we're going to end up with what kind of shape? It's going to be a rising snake, which is going to go up, up this way, down, down this way. It's a rising snake. So what's going to happen? We go up to, all right, well, here's -1. At -1, we have an x-intercept. -1 is a zero of multiplicity 1. Because the multiplicity is odd, what do? Do we cut or bounce? We cut, because 1 is odd. We cut. The exponent is even on the factor, we cut.
The exponent is odd.
Now, I don't know where this graph peaks, but I do know it's got to fall down to earth because we have another 0 at x equals 4. So I don't know where it peaks, but it's got to come back. We get another x-intercept at x equals 4. The multiplicity there is even. The multiplicity there is 2. 4 is a real zero of multiplicity 2. Now, because the 0 is even, that means that the graph is going to bounce off the x-axis. The graph's going to bounce off of the x-axis. Okay. All right, so the graph bounces. All right. It's a rising snake. It goes on, 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 on. And this is a basic sketch of the graph. X-axis here. Y-axis, but I don't know if the peak is going to be in quadrant 1 or quadrant 2. Let's see what Desmo says. Y equals the square of x minus 4 all times the factor x plus 1. So what's happening? The graph comes up from hell at 4, 0, and at -1, 0, there are x-intercepts. The graph comes up from hell at -1, 0. Exponent is 1. The graph cuts through the x-axis. It turns out the graph peaks here. We have a local max point in quadrant 1, but I didn't know if it was quadrant 1 or quadrant 2. On homework, I wouldn't expect you to know that. It turns out to be quadrant 1. That's where the derivative is 0. The graph comes down. We have another x-intercept at 4, 0. The exponent there is even, though, at x minus 4. Bounces. The graph goes up, up, up. Overall, we have a rising snake. Also, what else do we know? Well, if you plug in x equals 0, or if you expand it all out, you'll see that the constant term is 16. That tells us what? That tells us that 0, 16 is the y-intercept. So we know a lot about this graph. We know about the intercepts and the overall long-run behavior. That might be all we need to know. Now question. Again, here's another version of this sketch graph. What if we put the square on the other factor? All right, so let's take a look at f of x equals x minus 4 to the first, and then x plus 1 with that squared. What is this going to look like? All right. If you expand it out, we get x cubed and then lower order terms. All right, overall it's going to be a rising snake again. Up, up this way, down, down that way. Again, we have x-intercepts at -1 and at 4. Now this time, as we go up to the x-intercept at -1, 0, since the exponent is even, the multiplicity is even, that means we do what? Do we cut or bounce? Since the multiplicity is even, we're going to bounce. We're going to bounce. So we bounce. If you plug in x equals 0, we end up with -4. So 0, -4 is going to be our y-intercept over here. The graph's going to turn around. I don't know if the graph turns around in quadrant 3, but let's assume it's quadrant 4, right? Comes back up, and then x equals 4, it happens. Well, since the graph's going to go up, 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 I think it's going to cut, and it's going to cut. 1 is odd multiplicity. That means we cut through like a snake. We bounce like a bull over here at -1. Here at x equals 4, we cut like a snake, and then up, up, up. And lo and behold, let's graph that. Y equals, it was x minus 4 times x plus 1, and that's squared. Yes, we have a rising snake overall. We go up to the point -1, 0. We bounce. We have the y-intercept at 0, -4. It turns out that the midpoint is in quadrant 4, not quadrant 3, but in calculus you'll find that out. Then we go up, up, up. After the midpoint, we go up, up, up. And then at 4, 0, we cut. And then we go off, 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 like a rising snake. All right, so we know a lot about these graphs. And by the way, you're allowed to put a non-zero constant in front. What if we multiply by 2? Stretches the graph. By 3, by 4, and so forth, stretches. 0.5, that's a squeeze. 0.4, 0.3, 0.2, 0.1, that's a vertical squeeze. But still, the x-intercepts stay the same. The x-intercepts stay the same. And we still have the same bouncing and cutting behavior and the snake behavior. What about a negative number? What happens? If I multiply by -1, what happens? Upside down. But same x-intercepts. And we still bounce here, we still cut there. But this time, it's a falling snake. And the y-intercept also gets flip-flopped to 0, +4. Right. And then -2, -3, we stretch. But I put A out here, all right? I have the same x-intercepts, same bouncing and cutting behavior, rising snake here, falling snake here. If I put the square over here, we get those other guys. And that corresponds to all, so let's do that. I'll put the square over here, cut this out, all right? All right. So we get all these guys. And together, these form all the possibilities that will satisfy these specifications. Third-degree polynomial function in X with only 4 and -1 is zeros. We looked at all the possibilities. Wow. All right. And again, the even and odd multiplicities, they correspond to bulls and snakes, basically, locally, around the x-intercepts. So the graph is kind of like a snake near -1, 0 here, and kind of like a bull, and kind of like a bull at 4, 0 over here. All right. Next, a few final comments.
Okay. Let me, whoops, go back. Okay, I don't want to make a comment in chat. So, so if you have a factor like, oh, I don't know, x minus 2 all to the third, the multiplicity would be 3 at x equals 2. So at the x-intercept 2, 0, the graph cuts like a snake. Now, for all practical purposes, you're not going to get too many multiplicities beyond 1, 2, maybe 3. And remember, the higher the multiplicity, the flatter the graph is. And only high-degree polynomials can have like high multiplicities, right? But basically, it's really the whole odd-even thing. So like at x minus 2, if the exponent's odd, you cut like a snake. If the exponent's even, you bounce like a bull. I know I made a misstatement once in my lecture. Yeah, so it's good to review the lecture, although I'll need to post that correction. Remember, look at my video comments, because sometimes I note corrections if I misstate something. All right, so we're done with the bulk. The remaining 2 videos are mostly a slight extension. Part G, don't freak out about, and the last part is a recap, and then we'll take questions. Okay, and feel free to chat with more questions. All right, let's go on.
And cutting the search space in half.
Whoops.
Hi, everyone. Let's say you want to find a real 0 for a 10th degree polynomial function. One of the dirty secrets of mathematics is that we often have to use computer algorithms to help us approximate zeros of functions. So a computer spits out an approximation. Now, we don't have anything like the quadratic formula for 10th degree. We kind of do for 3rd and 4th degree, but nothing for 5th degree or beyond. So what could we do? Well, polynomial functions are continuous. The graphs are unbroken. So what we could do is the following. Let's say that we know that f of 2 is positive. The y-coordinate here is positive. Let's say we know that f of 8 is negative. Then because the graph is unbroken, there has to be an x-intercept somewhere in between. There has to be a real 0. So what could we do? Split the difference, take the midpoint, test to see what f of 5 is. Let's say f of 5 is positive. Then we cut the search space in half. We now know that a real 0 has to be between 5 and 8. And so forth. We can keep cutting the search space in half until we get an interval that's so tiny, we take the midpoint and go home. So that's kind of a dirty way of doing it, but that's a way of getting an approximation for a real 0. That's called the bisection method, because we keep bisecting and cutting the search space in half.
Okay. So don't worry about that for the homework, but I just wanted to show you how a computer algorithm can be used to approximate zeros. And again, a dirty secret in applied math is that, hey, we don't have exact formulas like the quadratic formula very often. We just have to plow something through an algorithm and get an approximation. And this is just for 1 0. All right, and you have to start with seeds where, okay, we have to know values where the function is positive versus negative. Anyway, don't freak out about that. The next part is a recap. That's the last video for 2-2.
Hi, everyone. So how do we graph polynomial functions? Well, you better know how to graph constant, linear, and quadratic functions. We've covered those. Also, some important points. Intercepts. Y-intercepts are easier to find, plug in x equals 0, but for x-intercepts, you have to find the real zeros of the function. That can be harder. That involves solving an equation. Symmetry. If the function is even or odd, you may be able to exploit symmetry. The zoom out dominance property. Look at that leading term. Based on the leading term, do you know what kind of snake or bull you're getting? And you can determine long run behavior. Where is the function positive versus negative in value? So for example, let's say they are graphing something like this. You know that the leading term is x cubed. That means you have a rising snake. That means that you have to be negative in y coordinate way out here. You have to be positive in y coordinate way out here if you're going to have a rising snake. a polynomial rising snake. If you know the factorization, then you can really know what's going on. The real zeros correspond to the x-intercepts. We see here they're 4, -1. And these are the only places where the function can change sign. Remember, a polynomial function can only change sign at its zeros, corresponding to the x-intercepts. But does it have to change sign? Not necessarily, because the graph can bounce. So a polynomial function can only change sign, but doesn't have to. Can, but doesn't have to change sign at the x-intercepts, or the real zeros. If the multiplicity is odd, then the graph cuts like a snake, and the function value, the y-coordinate, changes sign, here from negative to positive. If the multiplicity is even, then the graph bounces like a bowl off the x-axis, and we stay from positive to positive with 0 in the middle. So if you know what the leading term is, and if you know the complete factorization over the reals, then you should be able to know where the function is positive versus negative. And of course, it's 0 at the real zeros, the x-intercepts. When in doubt, there's point plotting as a last resort. And by the way, what is the range of any odd degree polynomial function? If you have 3rd degree, 5th degree, 7th degree, or 1st degree, what's the range? It's going to be all reals. You pick up all real values as y-coordinates. Can an even degree polynomial function have the same range? No. There has to be some sort of extreme point. In the long run, it's a bowl. There has to be some sort of extreme point. That's all for now.
All right, so that's that. 2.1 and 2.2, some nice ideas. So I thought people could handle it before turning in the chapter 1 homework. The ideas aren't too bad. It's just a lot of them. All right, so I have 913. All right, so I have 913. Of course, you're free to go, but, well, you're always free to go. But I will stay around for questions. I wanted to have some time for questions, all right? So we have about 17 minutes for questions in class, and I should have time to stay beyond. Okay, sometimes I have to go at 10 or so, but I think I can stay after a fair bit. Let's see. Right, okay, so I can take questions. Okay, now are there any questions in general? Any questions in general? Okay, now I'm recording. I think that students appreciate the recording, but let me know, privately maybe if you'd like me to stop recording. But I'll keep the recording going. Okay, so, unless you tell me that you prefer more private. Okay, so so I'll see some of you later. I do see some requests here. Okay, so let's see. Oh, and by the way, we will have time on Thursday also, about 50 minutes in class, and then maybe some time after. Okay, so I see here. Let me get maybe a text screen up. Okay, so 1.10, numbers 4 and 5. Okay, so I'm going to take a list of a few problems here. Okay, so I see, let's see, 1.10, numbers 4 and 5, 1.9, number 9. Okay, so anyone else want to add to the list now? Otherwise, I'll go ahead and start. You can keep going in chat. All right, so let's take a look at the homework. Okay, I see 172D. Okay. You can do it public or private, doesn't matter. All right. So first off, okay, 1.10, 4 and 5. Let's go all the way here. All right. All right, right. Okay. And these are problems that perhaps confuse people the most in this chapter. Simplify the difference quotient completely. And this might be worthy of its own whiteboard. Let's see, do I have a... Okay, I'll just grab a whiteboard. There we go. All right. All right, let's get a bunch of these whiteboards here. All right. Okay, so let's do 1.10 number 4. Oops. All right. So to simplify this difference quotient, all right, now take a look here. When you see something like f of x plus h, all right, what are we thinking? We're thinking what S word. Whenever we have f of something, we're evaluating, we're thinking substitution, all right? So when you think about that, what f of x plus h is, right, a lot of students just write, oh, I guess it's 1 over x all plus h, and that's wrong. Okay, don't just tack on a plus h. It's a substitution. You're substituting the x with an x plus h. So the upper left is 1 over x plus h. It's the reciprocal of x plus h. F is the reciprocal function. Minus the given rule, 1 over x, all over h. Okay. Now, for a lot of students, this is half the battle, just writing the original expression. That's worth some good partial credit right there. All right. And then comes the algebraic manipulation, right? So how do we resolve this thing? We don't like it right now because it's a compound fraction, right? So how do we resolve that? There are different ways of doing it. Some people might make the top part a single fraction. And actually, come to think of it, some people might prefer that. Another way to do that is that you can multiply by the LCD. You can multiply by this, which will end up clearing the little denominators there, over its twin. All right. Okay, so I'm going to ask the student, let me check here. See, would you prefer making the top a single fraction or multiplying top and bottom like you see in purple? And either way is fine. I'm asking particular students what might be more appropriate. Okay, okay. So I'm seeing a vote for multiplying top and bottom. Personally, I like that, but you do need to feel comfortable with the distributive property. And it depends if you can cancel things well in your head. If you're not as good as at canceling in your head, then it may not be as good. And again, if you want to make that top a single fraction first, that's fine also. All right, so here's one strategy. We can do the other if you want. Okay, so we're distributing. In fact, I'm going to show you the distribution. It might take some time, but it might help people. So I'm going to take the 1 over x plus h, and it's going to get both the x and the x plus h. If you want to be really careful, you can write these things out. But if you do this mentally, I'll believe you. Minus 1 over x, and again, you get both those factors. You get the x and the x plus h. Over h, and sorry folks, but you're going to need these guys as well. Even I forget those sometimes out of wishful thinking. Don't forget the guys in the bottom right. All right. And I hope you agree that that's correct. Are there any questions? You agree that's correct? I haven't miswritten anything. You all agree that's correct. All right. Now, again, you can do this part mentally, but take a look at the upper left. Upper left. What cancels out? Do you see what divides out up there? Well, the x plus h gets knocked out by the x plus h. For good measure, I'll put little ones here. Could be in parentheses. right? So x divided by x plus h is 1. And don't worry about domain right now, right? Over here, what cancels out? Well, x divided by x leaves 1. Right. Now again, you could do it mentally. If you multiply this upper left fraction by both these guys, the x plus h knocks out with this guy, and there's an x remaining. Minus, okay, you have 1 over x being hit by these two guys. The x's knock each other out. You have x plus h remaining. But now I'm going to be very careful when I write this next step out. Upper left, we just have a lonely x. Minus, okay, now a lot of students might write x plus h, but what do we need? What do we need? It's something that we often need a lot of in pre-calc. We need grouping symbols, or distribute the -1 immediately. We need grouping symbols, all right? That is one advantage to writing things out, because I think you're more inclined to put the grouping symbols if you actually write it out. But remember, if you're subtracting something with potentially more than one term, then be prepared to put grouping symbols. And here, we really need them. Or you can distribute the -1 right now. Also, we have the bottom. hx and x plus h. So if you get up to here, students for the most part are able to get this. If they can get up to here, we're 85% of the way there. Now, are there any questions? Are there any questions? Again, the idea is that we're simplifying this difference quotient. It is going to take some time. It has taken some time. Actually, you don't have to write that much, but you have to think it through. You have to be careful. All right, any questions? Okay, let's go ahead and distribute the -1. You could have done that here, but I want to be super careful. We get x minus x, what? Multiplying that -1, it's a minus h. A lot of people mess that up. It's a minus in here. All right, and that's an h. All over. Now you might be going, oh, you might want to distribute because students like to show off. No, don't do that. We like factored forms because then you're more likely to cancel. If you have more than one term on either the top or the bottom, then you really shouldn't be doing top-down canceling. So we like having factored forms there. I know students are just itching to distribute, but don't do that because then you'll just have to factor back. Don't do something just because you can do it. Don't try to show off. You'll have to. You're doing more work than you have to. Keep that in factored form. Now, on the top, who survives? On the top, who survives? X minus x is 0. That all gets knocked out. On the top, we just have the opposite of h over that factored denominator. And we're pretty much one step away. Because what can we now do? What can we now do? H is a factor on the top. H is a factor on the bottom. We can do some division. One way you can look at it, -1h divided by h leaves a -1. All right, that might be easier to write out. -1h divided by h is -1. Okay. Because otherwise, if you scratch the h's, you might not know if that guy's there or not. We saw the guys on the bottom. All right, so in the end, take a look at this. This is very nice. Equals -1 on top. We normally pop out the negative sign. 1 over x and x plus h. I'll accept that. Remember, in the canceling process, we're hiding the fact that h cannot be 0, but we're not really messing with domain anyway. Still, we have that hidden restriction. All right. So that's a good problem. I want to keep it. I'm glad I named it. I want to keep it. Any questions about that? Any questions? And if you understand the substitution principle up here in the upper left, that'll help you a lot in the other two problems. Substitution. Don't just go yeah plus h. That's wishful thinking. Questions? Questions? All right. Now I'll make a deal with you. I know that number 5 was also requested. I'll start this off. I'm going to start off number 5, and then I'll give you a hint, and then maybe we'll come back to it either later today or tomorrow, Thursday. Could be tomorrow, office hours. So if f is the square root function, all right. Again, what S word are we thinking? We're thinking substitution. So what's this guy? It's going to be the square root of. You're substituting the x with x plus h, but it goes on the inside. Okay. If this simplifies to something like a 1, you probably made a mistake, like not substituting. It's root x plus h minus root x. That's all plus 8. That's all over h. All right. Now, I'm going to give you a hint, and then maybe come back to me later today or on Thursday or office hours. What are you going to do? Rationalize the numerator. So make it to this step. That's a good first step. And then I'm going to tell you to rationalize the numerator. That means you multiply top and bottom by the conjugate of this guy. That's the guy with the plus sign. All right. So that's those are some hints there. Okay. Okay, 1.9, number 9. So I have all these whiteboards here. Okay, 1.9, number 9. All right. So let's see. And again, on the problem we did in number 4, I have no preference. Just show work and do it appropriately. I have no preference. Whatever makes you comfortable, show appropriate work. All right, so yeah, I went back down here. Let me go. 199. Oh, yeah. Okay. Well, what I'm going to do is I'm going to give you some key hints, okay? And then you might be able to figure it out. So let me give you some key hints here. Right. And then we can talk either tomorrow in office hours or Thursday if necessary. All right, on part A, I'm asking, develop a linear rule for f of x. So we want to develop, it's a linear function rule that'll convert us from Celsius to Fahrenheit. So x is in degrees Celsius. We want the function value to be the corresponding temperature in degrees Fahrenheit. It's temperature conversion. Okay, and now for example, 0 degrees Celsius goes to 32 degrees Fahrenheit, and 100 degrees Celsius goes to 212 degrees Fahrenheit. So what does that mean? That means that the graph has to go through these 2 points. We need to find the equation of the line for the points 0, 32, function values are y coordinates, and 100, 212. So then it falls back to a 0.14 problem when we talked about lines. So I hope you remember from section 0.14, you can review it. Given 2 points, 2 distinct points in the xy plane, find an equation for the line connecting those 2 points. That's a 0.14 skill. Okay, but if you understand that function values are y coordinates, you understand that these are 2 points on the line that we're talking about. Okay, and therefore you can find I guess slope intercept form. Since we want to have a rule for f of x or y, we'd like y equals mx plus b. You're basically looking for slope intercept form. Y, or f of x, equals mx plus b. All right. So that's a sketch there. Although, hold on. There are other parts. Let me see if I can help over here. Okay. So, okay. Some hints on B. I'll give some hints. And again, we can go over these in detail later. In B, it's a similar idea. Okay, except here, for the inverse function, the point 32, 0 is on the graph. The point 212, 100 is on the graph. So actually, B is going to be very similar. Part B is going to be very similar, except this time, you want to find the equation of the line that goes to the points 32, 0 and 212, 100. Again, you want slope-intercept form, y equals mx plus b. But it'll be a different line, though. It's going to represent the inverse function. All right. And then in the other two parts, I ask you to find f inverse of x using the conceptual method and the mechanical method based on the notes. But I hope I gave you a good running start. These are more standard, but again, we can talk in office hours or discuss in class Thursday. So yeah, we're starting off with some hints today. Okay. Let's see. So going to 172D. And again, if you'd like me to elaborate now, feel free to let me know. All right, 172D. So I'll save this. Okay. By the way, it's 9:32, but I will go on. It's just that if some of you have to go, it's 9:32. All right. D. Okay. Yes, and I can see why this is confusing for people. All right, so we're looking at h of r equals r cubed plus 1. Now, as a shortcut, we should be able to tell, since it's a nice polynomial in descending powers, if it's even, odd, or neither. So here's how I'm going to look at it. This is r to the third. That represents a nice odd function, plus 1 r to the what? R to the what is 1. R to the 0. But here's the problem. 3 is odd, 0 is even. We have a mismatch. This thing is neither. And you can see that from a graph. If you look at Desmos, here's y equals r cubed. All right? That's odd, symmetry about the origin. But if you add a plus 1, we lose that symmetry. We have neither the even nor the odd symmetry. This thing's a neither. This thing's a neither. If the function is neither, show why it is neither even nor odd. Actually, I would accept this, but technically it would be by a counterexample. Technically, you would see that h of 1. Okay, so here's technically how you would do it. H of 1 is going to be what? 2, if you plug into here, right? And what's h of negative 1? H of negative 1 is going to be 0. So right there, we're dead. Because here's the deal. The point 1, 2 lies on the blue graph, the graph of interest. The point negative 1, 0 lies on the graph of interest. So here's the problem. We have two opposing values for x, but the y coordinates are neither equal, so the function cannot be even, and they're not opposites, so the function cannot be odd. So this counterexample alone shows us that the function is neither, even or odd. All right, and feel free to chat comments or questions if you have any comments or questions. All right, some more here.
Yeah, quick question, sorry.
Go ahead.
So in an even function, the reflection about the y-axis, does it ever matter?
Well, yeah, remember, an even function has to have symmetry about the y-axis, like the graph in black, y equals x squared. The thing is, though, if you go back to the blue graph here, right, we do not have symmetry about the y-axis. And in fact, the point 1, 2 and the point negative 1, 0 alone, that pair alone shows you lack the even property. Because in order for this graph to be even, we'd have to have something like -1, 2, for example, to be on the graph, or maybe 1, 0. In order to have any chance for this graph to be even, then we either have to have the blue point on the graph, or the red point has to be on the graph. And even then, that's not a proof that it's even. It's just one demonstration. But a single example cannot show that a function is even. However, a single counterexample is enough to show a function is not even. If f of 1 is 2 and f of -1 is 0, the function values are not equal. Therefore, there's no way this thing's an even function. Likewise, the function values are not opposites of one another. Okay. Now, if we had -1, -2 on the graph, there's a chance this thing could be odd, right? Or maybe 1, 0, right? Then there's a chance the graph could be odd. But with these 2 points, just because of these 2 points alone, they're supposed to be partners, but they're not helping me. The y-coordinates are neither equal, so the function can't be even, but neither are they opposites, so the function cannot be odd. Therefore, right now, I have proof that the function is neither. Because these 2 points alone, these supposedly partner points, they're not helping me. Well, they help me in the sense that I know that the function is neither. But these 2 points alone destroy any chance of even or odd symmetry.
Got it. Thank you.
Oh, you're very welcome. Yes. And I see how the neither case is confusing. Right. On homework or exams, I wouldn't expect people to do a counterexample, but that is technically the way you're supposed to do it. Actually, as far as work goes, I would accept this, just recognizing that you have a mix of exponents, even and odd. I'd accept that. Heck, if you know it's neither, that's great.
So if there's ever a discrepancy in exponents, it's automatically not symmetrical about the y-axis?
Well, correct. If you have a polynomial written in nice descending powers form, right? So no weird, you're taking squares of stuff and stuff like that. If it's nice descending powers form, then all you have to do is look at the exponents, all right? If they're all odd and there's no constant, remember, so if you have a constant term, put like r to the 0 next to it, okay? Indicate that power of r or x or whatever. But once you have all these powers of r, right? If all the exponents are odd, great, the function is odd. If all the exponents are even, great, the function is even. But here, 3 is an odd exponent, 0 is an even exponent, you're dead. That's in neither case.
Always neither?
Yes, if you have a mix of even and odd exponents for a polynomial, and very often for basic rational functions. Although for more complicated functions, it's usually best to look at h of opposite r and see what happens. But for polynomials, where you have descending powers, it's very straightforward. There's a very straightforward shortcut.
Thanks.
You're very welcome. Yes. Okay. Okay, where are we? Okay. Okay, so let me continue on this list. Yeah, 1, 4, I see number 6 is popular or unpopular, as the case may be. 1.4, number 6. Okay, especially A, but I'm seeing a request for all these. What I might do is I might start with A, and then let's see if we can get the flavor going, the rhythm. I think I know what these are, because many students ask about them. Okay, which group? Oh yeah, it was this one. Of course, right. Although 6 and 5 are kind of similar in flavor. In both of these cases, you're looking at the behavior of 1 or 2 particular points, all right, not the entire curve. Okay, so let's take a look at number 6. All right, a function f has 3 and 9 as its only zeros. Okay, let's say that we have a function, y is a function of x. Well, hypothetically, I know I use different letters here, but let's say we have y equals a function of x. All right. So what's the deal? The real zeros of the function correspond to what points on the graph? When y is 0, that means we're looking at what points of the graph? The x-intercepts. So what I'm saying is that if you graph y equals f of x, we are going to get x-intercepts at 3, 0, and 9, 0. And these are the only x-intercepts on the graph. Otherwise, I have no idea what the graph looks like. Okay, 3, 0, and 9, 0 lie on the graph. I know almost nothing else about this graph. So I'm basically tracing the behavior of these 2 points. That's usually what's happening. All right. So let's start with A. I'll start with A, and I'll briefly discuss B. And then as a challenge, let's see if you can analyze the others. All right, let's do A and discuss B. Let's do A. All right. Here's a graph of y equals f of x. Now in blue, I'm going to consider, let's do a text here. In blue, I'm going to consider in part A, let's consider y equals f of x minus 2, or what I'm calling g of x. So up here we have y equals something in x, with x in it. Over here, we have y equals, what you do is, when you go from x to x minus 2, you're doing a substitution. Okay, you're applying here a substitution. Then you're going, well, what do I substitute into? It's not a matter of doing it mechanically. It's the concept. It's the idea. Here's the idea. If you substitute x with x minus 2, whatever this graph looks like, what impact does this transformation have on the graph? If you replace x with x minus 2, everywhere you see x, what impact does it have on the graph? Okay, excellent, excellent. It's a horizontal shift, but be careful though. It's not to the left. Careful, it's not to the left. The sign surprises you. It's actually to the right. Be careful, the sign surprises you. But I'm glad you recognize it was a horizontal shift. That's part of the battle. So we end up with a horizontal shift. Oh no, don't say dud. I mean, it's tricky, right? The fact it's a horizontal shift, that's a big observation. But remember, the sign surprises. Okay, sometimes I forget this. Whoops. The sign surprises, and you get a shift to the right. Okay, because I know the minus sign, you're thinking left, but you got to fight your brain. It's actually shifting to the right. Just like if you go from, well, let's go to Desmos. Seriously, Desmos might help you with reviewing some things. Here's y equals the square root of x. It's your classic hook, right? What happens if you have, well, h equals the square root of x minus 2? See, in blue, that graph shifted to the right. So seriously, go ahead and play with Desmos and experiment. I want you to do that. That's what the homework's for. All right, which means, hey, folks, what does that mean? The x-intercepts at 3, 0, and 9, 0, guess where they are now? In fact, I can use this fake graph. They used to be at 3, 0, and 9, 0. What are these numbers now? What are these numbers now? 3 goes to
5.
And 9 goes to
11.
All right. So these are the new x-intercepts. Therefore, they're the new zeros for the transformed function g. That's the idea. See, before, in problem 5, I was asking you to trace the behavior of this one point, -4, 2. Otherwise, I didn't know the shape of the graph. This is kind of similar, except here, we're tracing the behavior of specifically the x-intercepts. But the flavor of this problem is very similar to what we saw in number 5. All right. Any questions about A? Because if you get A, you should get the flavor of this problem. Although, feel free to discuss with me in office hours or during Thursday sessions. I do actually want to touch on B because it's a different flavor from the other problems. And actually, even I didn't get it perfectly right. Even I made a late observation on this. B is an interesting problem. Let's talk about it. Okay. So the original graph, you had x-intercepts at 3 and 9. Now, I'll do that in purple again, just to be consistent. Oh, okay. You have an idea, but it's actually an interesting answer here. All right. So here's the old guy, right? We know it's only x-intercepts are at 3, 0, and 9, 0. And there's some graph. In fact, I'm going to make up a fake graph. Folks, I know that Sometimes we shouldn't make up things, but it's not such a bad idea to make up a graph to give you some orientation, right? Give you an idea. Now, Nick is on the right track. If you add 1 to the right-hand side, what impact does it have on the graph? When you graph y equals the new guy, h of x, what happens? What happens to the purple graph? You get that's correct, a vertical shift, and it is up by 1 unit. It is as expected, all right? I'm going to go to blue. So here's the new graph. I shifted up 1 unit. Well, what happens? Well, based on my picture here, I get 1 X-intercept, but where is it? And what if I had a different graph? Here's the thing. Would you agree with me that there are all sorts of different graphs you could have over here, and I'd get all sorts of different answers here? The answer to B is basically, we don't know. We don't know what the new zeros will be. Because here's the problem. Think about the movie Jaws, right? Who was the star of Jaws? Who was the star of Jaws? It was this monster shark underneath the ocean, right? Here's the problem. In order for me to know the new zeros, the new x-intercept, I would have to know what's happening 1 meter underneath the surface. And then these points here would rise up to the surface of the ocean. But here's the problem. I don't know what's happening 1 meter beneath the ocean. So I don't know what's happening right now on the blue graph. So you believe me that we should be humble. We don't know what's happening with the new graph because I didn't know what was happening underwater. Do you see what I'm saying? We don't know what happened underwater on the purple graph, so I have no idea what points down here might be moving up. Except there's one other thing, and I didn't realize this until I thought about it. There are a couple things we do know. There are a couple things we do know, and this is going to freak you out. When you graph a function, y is a function of x, what test must be passed? To have y as a function of x, what graphical test must be passed? The VLT, the vertical line test. Now, do you agree with me on this? On the purple graph, we know that, what was this? Oh, yeah. Okay, we know that on the purple graph, we know that 3, 0, and 9, 0 were on the purple graph. But that means that by the vertical line test, the point 3, -1 and the point 9, -1 cannot be on the graph. You agree with me? 3, 0 and 3, -1 cannot both be on the purple graph because then you fail the VLT. Same for x equals 9. You agree with that? Which means that the sharks cannot be at these 2 points. So, and actually, I didn't figure this out until like several semesters in. We don't know what the new zeros will be. However, I do know something. They cannot be 3 or 9. 3 and 9 cannot be zeros because the point 3, -1 and the point 9, -1 could not have been on the purple graph. Then we'd have failed the VLT. So problem B, I like problem B. It really makes you think, and I did not give a full response until later. So it even tricked me. I didn't realize, hey, wait a minute. You can say, at first I said you can't say anything. Actually, you can say something. 3 and 9 cannot be zeros. But beyond that, you can't say anything. But I do know that 3 and 9 cannot be zeros. That's from the VLT. So B is a good problem-solving problem. It's tricky, though. Bear in mind, the others aren't as tricky. The others are more of the flavor of A, where if you trace the transformation, you're in good shape. Okay. Okay, so I'll leave it to you to try to work out the rest of 6. If you have trouble, feel free to contact me and get an appointment with me for office hours on Wednesday, or we'll talk on Thursday. Yes, you're welcome. You're welcome. Do look at this problem. Let's see. So 1, 4, 3, 4, 5. Oh, 6C? Okay, I'll do one more. It's a different flavor because that's a non-rigid transformation. So I agree that's fair. I'm starting to run out of space here, so I need a new whiteboard. Okay. These whiteboards come in handy. I basically take screenshots of my preview files, but you got to PDF them. If you want to be able to move objects later, you got to PDF them. If you don't PDF them, then they're frozen. You can't move anything later. All right. Okay. set the markup toolbar, and we're doing C, right? 1, 4, number 6C. Let's look at a non-rigid transformation. But you see that's a similar flavor as A. It's not as bad as B. B's tricky. All right. Okay, now I'll go back to purple. What do we know about the original purple graph for F? Once again, we knew that the only x-intercepts were at 3, 0 and at 9, 0. These are the only x-intercepts. All right. Now, what about the graph for P? Okay, here we're considering the graph of, I'll put this in blue. Here we're considering the graph of y equals P of x, where P of x is what? F of 3x. So basically, now back here, this is in purple. Back here, we consider the graph of y equals f of x. Okay, back here, we're considering the graph of y equals f of x. I only know the deal with the x-intercepts. We're now considering the graph of y equals f of 3x. Now, if you remember your trig, again, decimals might be helpful here. If you remember your trig, if we had y equals sine of x, remember sine of x? Sine wave there? If you substitute, replace x with 3x, do you remember what happens to the graph? Do you remember what happens to the graph if you substitute x with 3x? The graph y equals sine of 3x, what happens? You get an accordion effect. What is that? When you go from the blue graph to the green graph, that's a horizontal squeeze. You're getting a horizontal squeeze towards the y-axis. It's like an accordion, right? You're squeezing an accordion or spring towards the y-axis. That's a horizontal squeeze. So tell me, if you're squeezing these x-intercepts towards the y-axis, where do you think the new x-intercepts will be? I'll give you a hint. On the same scale, they'll kind of look like this and this. Where does 3 go to? If x equals 3 over here, what does x have to be here to make the argument equal to 3? When x equals what? 3x is 3. When x equals what? Then 3x equals 3. When x equals
1.
1. All right. Now solve 3x equals 9. When x equals what? When will 3x equal 9? When x equals 3. Does that make sense, right? 3, 0 gets squeezed in to 1, 0. And 9, 0 gets squeezed into 3, 0. So you can either look at it from a sort of solve an equation deal, what makes 3x equal to 3, what makes 3x equal to 9, or visually, it's sort of let your common sense kick in. You're squeezing these x-intercepts towards the y-axis. You see a 3 there. So it kind of makes sense that these will be 1/3 of these over here. It's like a compensation. Right. Yeah, these problems are easy after you see a solution. But I don't blame students. They're tricky when you first see them. I know students are going, I don't get this notation. What do you even mean? Okay, so yeah, it's easy when you see it. Okay, but see if you can do the others, right? D, E, and F. See if you can figure those out. Good problem solving. And also getting used to this notation. All right. So let me check over here. Yes, you multiply each coordinate by 1/3. That's right. So whatever the x-intercepts would have been, you would multiply by 1/3. More than anything else, because I think even the solve the equation thing is kind of tricky, I wanted people to know that when you substitute x with 3x, like for the sine graphs, you're doing a squeezing in, like from the blue graph to the green graph. I mean, play with Desmos, right, to demonstrate this. I wanted people to know that there's a squeezing in. And if you look at the 3x, then your graphical common sense might say, you know what? I think the 3 is going to 1. I think the 9 is going to 3. Right. Although common sense doesn't always help. Sometimes you get surprises. If anything, this is kind of a compensation. There were some others. do we have to graph like you for? Oh, no. You don't have to graph. Although, for your benefit as a student, I would encourage students to draw graphs for themselves. But no, to be honest, for these problems, I will accept answer only, but I think it would help you as a student to understand why these things work. All right. But again, when you turn in homework, yeah, it is good to show work where appropriate, because I'm hoping that people get the rhythm from the notes and the lectures, how much work they should show. But I realize that students are kind of wondering, well, how much do I really need to show? Follow the notes, right? Follow the notes, follow the lectures. It turns out here I'll accept answer only, but I think it's good for the student to show some ideas for your benefit. Let's see.
I have a quick question. It's not really a problem to work through, more conceptual.
Right.
1.6, number 4.
Let's take a look at it.
So for any of these, right, when I was checking the answers PDF, I noticed the answer had g of x and f of u. I originally had written my answers g of x and f of x, even though I now see that in the question it mentions f of u. If I had just left it as g of x and f of x for the answer, would that still have made sense?
Okay, now on the homework, I'll accept that. On a test, actually, it's funny. On a test, I would put let g of x be blank and let f of u be blank. So on a test, if someone wrote the cube root of x, I might have taken off a point because they should match up. But because it was a fill in the blank type problem. But on the homework, if you do it freehand and you give f of x instead, I probably wouldn't take off. I might have the right to because I'm still mentioning f of u. But on an exam like Quiz 1B, I would often have f of u equals, and I have students fill in the blank. If they gave me like the cube root of x, I'd often take off a point.
Okay, I see. So, I mean, without this being stated in the question, the f of u portion, theoretically, what I had written down originally, g of x and f of x, it's still correct, right? Technically.
Yeah, I'd probably accept it for full credit. Although I still have the right to take off points because technically I'm asking you to find g of x and f of u. I'm kind of applying a fill in the blank. But I think on the test, I'd be a bit more harsh because it would actually be a fill in the blank. Whereas here, it's more that you understand the concept, right? Okay. Whereas here, if it's fill in the blank, if you're giving me a wrong answer for a fill in the blank, this is wrong. I mean, this is just outright wrong, right? Yeah.
Got it. So, I mean, it's not, it's just in the wording of it. So if it hadn't been mentioned in the wording of the question, it wouldn't have technically mattered.
I'll put it this way. Still, because I'm asking for f of u, you should technically put like the cube root of u. Okay, you should do that. And technically, I'd have the right to take off points, but I don't think I would because I'm focusing on the concept here. On an exam, if I give a fill in the blank problem, and you say f of u equals the cube root of x in a fill in the blank problem, that's a problem because this is outright wrong. See, at least if you put f of x equals the cube root of x, even on the exam, I might have accepted this. So basically on the exam, if a student said, hey, I don't want to deal with f of u, I'm going to cross this out, and the student puts this instead, I'd be okay with that because you're being consistent. Awesome. See, because that's appropriate, right? You're saying f is the cube root function. This doesn't say that. This is a mess, right? Because you have mismatched inputs here. This is saying f is the cube root function. That's appropriate. So if a student on an exam were to cross this out and put this, I'm cool with that. And on the homework, you're basically doing that. Yeah.
Cool. Thank you.
Right. Okay. Let me see if there are other questions. 1, 4, 3, 4, 5. I see. Did I address those? 1, 4. Oh, here's 1, 4. Okay, so 3, 4, and 5. Okay, so here's the deal. I'll briefly discuss 3, 4, and 5. All right. Okay, on number 3, I'll give you some key hints here. So your coin, I gave a graph for this before, I think. When you graph the height, s of t versus t, your coin goes like that. You're graphing position against time. Now, if your friend, okay, waits 1 second and then drops the coin, your friend's graph looks like this. It's a horizontal shift by 1 unit. That's my hint. So try to run with that. Try to answer this question given that. Your friend's graph for capital S, I'll put big things here, okay? It's going to be shifted 1 unit to the right, and then you're going to answer this question. The domain will also be shifted to the right. Key hint. Number 4. The graphs below are obtained by taking basic graphs and applying rigid transformations. I'll do A, you try to do B. I'll do A. Over here, what's the basic graph? We have a hook here. What basic graph do you think I'm taking? Y equals the square root of x. Y equals the square root of x. But wait a minute. It's being translated. I'm applying rigid transformations. I'm not doing any stretching or squeezing. That's for trig. I'm only applying rigid transformations. Here, translations. So what's this guy actually? Y equals, it's being moved to the left. See the old graph looked like this. The old graph was a hook that started at the origin. But what's happening now? We're moving the hook 2 units to the left. So what do? We substitute or replace x with what? X.
+2.
Very good. X plus 2, because the sign is surprising. Excellent. X plus 2. Okay, we shift left. And then we move what? Up 3 units, correct? We move up 3 units. What do I put and where? What do I write? To shift up 2 units, 3 units. To shift up 3 units, what do I write?
+3 outside of the radical.
Very good. +3 outside the radical. You just straight up add 3 to the right-hand side. There you go. So you're taking the basic equation here for the basic hook graph, and you're translating to the left and up. For B, it's a similar process, but it's a different basic graph, and there's going to be a reflection also. So as a challenge, try to do B, although if you're frustrated, we can get back to it. On 5, let me say that 5 is kind of similar to 6. On 5, you're tracing the behavior of this point. I'll do A. Okay, I start the point -4, 2. I don't know what the rest of the graph looks like. Well, it passes the VLT, but whatever. Again, we did this before. When you substitute x with x plus 2, what happens to the graph? It's the same as what we did here. When you substitute x with x plus 2, what happens? Once again, we move 2 units to the left. This point moves 2 units to the left. What point's over here? After we shift 2 units to the left. That's going to be the point. What changes? X changes. It decreases by 2 units. -6, 2, correct? That's where the point moves to after this horizontal translation. What does the -5 do? Takes this point and does what to it? Takes this point and drags it way down, 5 units. So where is the final point? Where does the point end up at? The x-coordinate does not change, stays -6. The 2, that's what changes. The y-coordinate decreases 5 points, 5 units. 2 minus 5 is -3. That's your final answer. And on A, I might actually want to see some work. Either you stay what's going on or you draw me these pictures. Because I would like to see the intermediate point there. By the way, some people might be going down and then left. That's okay too. You can go either way. You can either go left and down, or you could go down and left. You do have commutativity here. When you do translations, you can do them in any order. But I would like to see either this intermediate point or this intermediate point at -4, -3. One or the other. Okay, and I'll leave it to you to consider the others. We can discuss further on Thursday or in office hours. Okay, I think I've hit the questions in chat. Are there any further questions? It's 10:06, but I can stay a bit longer. 8C. Oh, wait, sorry. I did 6C, right? Yeah. Oh, to kind of check to see if the points are going in the right direction, you mean? To see if the points are going in the right direction? Oh, you mean the square root graph? Yeah, I agree. Let's do that. Right. For the other students, let's do that. Y equals the square root of x, like you're checking your answer, right? You move left by 2 units. You substitute, you shift left. You shift left by 2 units. You substitute with x plus 2. To shift left by 2 units, you substitute with x plus 2. And to go up 3 units, you tack on a plus 3. That's correct. Good. And then the green graph is your final graph. Right. So yeah, Desmos is great for the square root graph. Yeah, right. Right. You don't have to do additional problems in 1/6. Were those the right, the domain of a composition? Yeah, because that's more complicated, right? So on a test, I wouldn't ask what's the domain of F circle G. I might ask what's the domain of H if H of X is kind of messed up looking. But the whole composite function thing, I think the main question is kind of confusing, and books don't even do it right. Okay, have I addressed the questions in chat? I think so. Anything else? I don't think I have to leave too early tonight, but okay, where can I find the record about the homework? Well, the homework answers are online. Is that right? Or the grades? I'll email grades. Bear in mind that I'm being very delayed. September is a tough month because I'm doing new videos. Now, my last week for new videos is next week. So I do hope I can get back to the grading late September. But yeah, the grading is being delayed. I'm going to email you the results. Okay. So yes, there's going to be a delay. October is going to be a big grading month for me. Apologies for the delays. September's tough. Any other questions? Any other questions? Oh no, it's no bother. I'm wide awake. I'm wide awake. I know you
Yeah, I have some, but I kind of feel bad that it's already 10, so I'll wait till Thursday.
Oh, don't feel bad. No. If you're tired, I don't blame you. But I'm wide awake. Go for it if you're up for it. If you're tired, I don't blame you.
Sure, let's knock one out.
Right.
1.9, number 2. Couple quick questions.
Yeah, Nick's right. I made this class late for a reason. I'm a Nighthawk. Don't worry about me. No, but it's just that sometimes I have to pick up a friend from work. That's the only thing. Like at 10, but that wasn't the case today. All right. Let's see. 1.9 number what?
So 2A, when I was drawing the table,
yes.
I was just putting the same inputs as F, the function F table.
Oh, so okay. Now
-2, 1, and pi in.
For F inverse.
Inputs for the F inverse.
Here's what you do. You switch the columns.
Right.
Switch the columns. So you have -8, 1 pi cubed for the inputs, -2, 1 pi for the outputs. You just switch the columns.
Okay. And for C, when it asked me to find the range, I wrote down the equation F inverse is the third root of X. And so I just wrote, all reals.
But here's the thing, though. See, I'm restricting the domain. The domain only consists of 3 numbers. The graph is just 3 points. It's just 3 points.
Okay. I need to start reading the questions.
Yeah. Oh, yeah. That's a good student skill. Yeah. That's the entire graph. That's the entire graph of this function. The domain only consists of 3 numbers. So now again, the inputs and the outputs, those columns are switched, right? So Inputs are -8, 1, pi cubed. Hard to draw pi. Negative, and then outputs, -2, 1, pi. Now, in part C, I'm asking you, what's the range for F inverse? Remember, what's the range? Is it the set of inputs or the set of outputs?
Inputs for the inverse.
Well, it's, okay. Now,
output for the inverse.
yeah. Now, remember, range always corresponds to outputs. But the point I'm making is that the outputs for the inverse function were the inputs for the original function. I know it's confusing. Right. Remember that range always refers to outputs. It's just that the range for the inverse function is the domain of the original function. Yeah. It is confusing. I'll be honest. I get confused all the time because I have a hard time with left, right. I can't dance, right? So it's like I always get left, right confused all the time. But that's the idea. Range is always outputs.
And also 3a and b.
On this section? Right. Okay. Oh, okay. So in 3a, here's the deal. These are both functions because they pass the vertical line test. Okay. But how can we tell if they're one-to-one functions if they also pass what other test?
Horizontal.
The HLT. So that's the question. Which of these pass the HLT or not? If you pass the HLT, you're also one-to-one. If you don't, you're not.
So one-to-one is when a function is valid when you invert the x and y?
Well, a function is one-to-one such that if you switch inputs and outputs, you'll still get a function.
Okay.
Right. And the only way that happens, see, here's the deal. Here's a nice way to look at it. When do you have a graph of a one-to-one function? If the graph passes both the VLT and the HLT. If it passes the VLT, you have y as a function of x. It's a function. If it passes the HLT, not only is it a function, it's what kind of function? It's 1, 2, 1, and therefore invertible.
Okay, so just b is one-to-one here.
Correct. So this guy, he's kind of a cubic looking guy, right? Yeah, this guy is a one-to-one function, therefore it has an inverse function. This guy fails the HLT. This does not have an inverse function. Now, some books might say it has an inverse, but it does not have an inverse function. It has an inverse relation, but it doesn't have an inverse function.
Got it. Thanks.
Because, for example, when you go backwards, this y coordinate goes back to multiple x coordinates. You got to be able to go backwards, and you can't have multiple outputs when you go backwards.
And number 4 is my last one for tonight.
Okay. Now, what do I mean? Now, when I say that a function is increasing on the reals, what does that tell you about the graph? If I tell you that I have an increasing function, do you know what that means about the graph? The graph is always doing what? It's always going up. Kind of like y equals x cubed. Or for that matter, y equals x. I mean, I can just say y equals x. That's an example of an increasing function. Also, y equals x cubed. Sorry, x cubed. X squared is not solely increasing. Y equals x cubed, y equals x to the fifth. These are all increasing. Okay? Now, they're functions. The graphs pass the VLT. If they're increasing, they're also going to pass what other test? The HLT. I know it looks very flat here, but you even pass the HLT near the origin. I know it's flat, but it's very flat looking, but you are passing the HLT. So therefore, passes the HLT, therefore it's one-to-one and invertible. Yes to both. If you're increasing, you're not allowed to go flat. A point on the right must be higher than any point to the left. You're not allowed to go flat.
Technically, for like a parabola, if the r is when you say increasing on r, can you mean like increasing from -1 to -10?
No. See, here's the thing. So for y equals x or x to the third, right? We can say that we're increasing on the reals. Any point on the right is higher than any point on the left. Okay, regardless of whether you're talking positive values or negative values for x or whatever. But if you have y equals x squared, here's the problem. The function here is increasing on the non-negative reals on the right here, but it's decreasing on the negative reals. or the non-positive reals. So here's the problem. The squaring function, it's not increasing on the reals. It's only increasing on part of the reals. That's not enough.
Okay.
Right. And you can see here, we have a problem, right? This guy fails the HLT. As it stands, it's not one-to-one or invertible. Now, if you restrict the domain, right? If you restrict the domain, so it looks like that, then it works. If you restrict the domain, then this thing is increasing on the domain. And we're good.
Not all invertible graphs are one-to-one though, right?
No, you need the one-to-one property. All invertible functions must be one-to-one.
Oh.
Yes. Remember, when I say invertible, it means you have a one-to-one function. Now, some books might talk about inverses as inverse relations, but no. Most books say, and I say, when we say invertible, you have an inverse function, which means that when you reflect about the line y equals x, the result also passes the VLT. See, here's the problem. If you try to reflect y equals x squared about the line y equals x, whoops, you get this graph, x equals y squared. That graph does not pass the VLT. See, the problem with a graph that fails the HLT is that when you try to reflect it about the line y equals x, your attempted inverse graph is going to fail the VLT. And we can't have that for an inverse function. You see? It's an inverse relation, but it's not an inverse function specifically. So in this class, inverses are inverse functions. If the original graph fails the HLT, then the reflected graph will fail the VLT, and you're dead. There's no inverse function.
All right. It's a little harder to grasp this, so I'm going to keep working.
Yeah, inverse functions are confusing. I agree. But remember, only one-to-one functions have inverse functions. Your graph has to pass the HLT for your reflected graph to pass the VLT to be a function.
That's a good rule there.
Right. See, these are inverses as relations, but not as functions. This isn't a function over here.
All right, that's it for me for tonight. Thank you.
All right. Yes, thank you for your hard work and your commitment. Yes, thank you. All right. Are there any other questions?
Yeah, that's it for me too. Have a good night, Professor.
Okay. Have a good night. All right.